Warning: empty page. Digital design with an introduction to the Verilog HDL, VHDL, and System Verilog. This page intentionally left blank. Digital design with an introduction to the Verilog HDL, VHDL, and System Verilog 6th edition Global Edition M. Morris Mano. Emeritus Professor of Computer Engineering, California State University, Los Angeles Michael D. Ciletti. Emeritus Professor of Electrical and Computer Engineering, University of Colorado at Colorado Springs, 330 Hudson Street, New York, New York, 10013. Senior Vice President, Courseware Portfolio Management, Marcia J. Horton Director, Portfolio Management, Engineering, Computer Science, and Global Editions, Julian Partridge Higher Ed Portfolio Management, Tracy Johnson. Dunkelberger, Portfolio Management Assistant, Christy Alora, Assistant Acquisitions Editor, Global Edition Auditi. Agarwal, Assistant Project Editor, Global Edition, Orko Mitra, Managing Content Producer, Scott DeSano, Content Producer, Robert Engelhart, Senior Manufacturing Controller, Global Edition, Kay Holman. Web Developer, Steve Wright, Media Production Manager, Global Edition, Vikram Kumar, Rights and Permissions Manager, Ben Farini, Manufacturing Buyer, Higher Ed, Lakeside. Communications Inc., LSC Mora Zaldivar Garcia, Inventory Manager, and Lamb Marketing Manager, Demetrius Hall, Product Marketing Manager, Yvonne Venata, Marketing Assistant, John Bryant, Cover Designer. Lumina Datamatics Incorporated, Cover Photo, Spainter_VFX / Shutterstock, Full Service Project Management, Vimla Vinaykam, SPI Global. Credits and acknowledgments borrowed from other sources and reproduced, with permission, in this textbook appear on appropriate page, within text. Pearson Education Limited, KO 2 KO Park Harlow CM17 9 NA, United Kingdom and associated companies throughout the world. Visit us on the World Wide Web at www.pearsonglobaleditions.com. Copyright Pearson Education Limited, 2019. The rights of M. Morris Mano and Michael D. Ciletti to be identified as the authors of this work have been asserted by them in accordance with the Copyright, Designs and Patents Act 1988. Authorized adaptation from the United States edition, entitled Digital Design, with an introduction to the Verilog HDL, VHDL, and System Verilog, 6th edition, ISBN 978-0-13-454989-7 by M. Morris Mano and Michael D. Ciletti, published by Pearson Education. Copyright 2018. All rights reserved. No part of this publication may be reproduced, stored in a retrieval system, or transmitted in any form or by any means, electronic, mechanical, photocopying, recording, or otherwise, without either the prior written permission of the publisher or a license permitting restricted copying in the United Kingdom issued by the Copyright Licensing Agency Ltd, Saffron House. 6-10, Kirby Street, London, EC1N, 8TS. All trademarks used herein are the property of their respective owners. The use of any trademark in this text does not vest in the author or publisher any trademark ownership rights in such trademarks. Nor does the use of such trademarks imply any affiliation with or endorsement of this book by such owners. British Library Cataloguing in Publication Data. A catalogue record for this book is available from the British Library, 109876543321. ISBN 10-1-292-23116-5 Typeset by SPI Global. ISBN 13-978-1-292-23116-7 Printed and bound by Vivar in Malaysia. Contents Preface 9-1-digit ALSYS Thames and Biner Y numbers 17.1.1 Digital Systems 17.1.2 Binary numbers 21.3 Number base conversions 22.1.4 Octal and hexadecimal numbers 25. 1.5 complements of numbers, 27 1.6 signed binary numbers, 33 1.7 binary codes, 38 1.8 binary storage and registers, 47 1.9 binary logic, 52 Boolean algebra and logic gate S57, 2.1 introduction, 58. 2.2 Basic definitions, 58, 2.3 Axiomatic definition of Boolean algebra, 59, 2.4 Basic theorems and properties of Boolean algebra, 60, 2.5 Boolean functions, 66, 2.6 Canonical and standard forms, 72. 2.7 Other logic operations, 81, 2.8 Digital logic gates, 83, 2.9 Integrated circuits, 89. 3 Gate level minimization, 98, 3.1 Introduction, 99, 3.2 The map method, 99, 3.34 Variable K-map, 106, 3.4 Product of sum simplification, 111, 3.5 Don't care conditions, 115. 3.6 NAND and NOR implementation, 118, 3.7 Other two-level implementations, 126, 3.8 Exclusive OR function, 131, 3.9 Hardware description languages, HDLs, 137, 3.10 Truth tables in HDLs, 154. 4 Combinational logic, 163, 4.1 Introduction, 164, 4.2 Combinational circuits, 164, 4.3 Analysis of combinational circuits, 165, 4.4 Design procedure, 169, 4.5 Binary adder subtractor, 172, 4.6 Decimal adder, 184. 4.7 Binary multiplier, 186, 4.8 Magnitude comparator, 188, 4.9 Decoders, 191, 4.10 Encoders, 195, 4.11 Multiplexers, 198, 4.12 HDL Models of combinational circuits, 205, 4.13 Behavioral modeling, 231. 4.14 Writing a simple test bench, 239, 4.15 Logic simulation, 245, 5 Synchronous sequential logic, 261, 5.1 Introduction, 262, 5.2 Sequential circuits, 262, 5.3 Storage elements, latches, 264. 5.4 Storage elements, flip-flops, 269, 5.5 Analysis of clocked sequential circuits, 277, 5.6 Synthesizable HDL models of sequential circuits, 291, 5.7 State reduction, and assignment, 316. 5.8 Design procedure, 321 6 registers and counters, 342 6.1 registers, 342 6.2 shift registers, 346. 6.3 Ripple counters, 354 6.4 Synchronous counters, 359 6.5 Other counters, 367 6.6 HDL models of registers and counters, 372 7 Memory and programmable logic, 393 7.1 Introduction, 394. 7.2 Random access memory, 395 7.3 Memory decoding, 402 7.4 Error detection and correction, 407 7.5 Read-only memory, 410 7.6 Programmable logic array, 416 7.7 Programmable array logic, 420. 7.8 Sequential programmable devices, 424 8 Design at the regist are transfer leave L, 445 8.1 Introduction, 446 8.2 Register transfer level, RTL, notation, 446 8.3 RTL descriptions, 448. 8.4 Algorithmic state machines, ASMs, 466 8.5 Design example, ASMD chart, 475 8.6 HDL description of design example, 485 8.7 sequential binary multiplier, 503 8.8 control logic, 508. 8.9 HDL description of binary multiplier, 514 8.10 design with multiplexers, 529 8.11 race-free design, software race conditions, 545 8.12 latch-free design, Y-way silicon. 548. 8.13 System Verilogin Introduction, 549 9 Laberator, Y experiments with standard ICs and FPGAs, 571. 9.1 Introduction to Experiments 571. 9.2 Experiment 1 Binary and Decimal Numbers 570. 9.3 Experiment 2 Digital Logic Gates 579. 9.4 Experiment 3 Simplification of Boolean Functions 581. 9.5 Experiment 4 Combinational Circuits 583. 9.6 Experiment 5 Code Converters 584. 9.7 Experiment 6 Design with Multiplexers 586. 9.8 Experiment 7 Adders and Subtractors 588. 9.9 Experiment 8 Flip-flops 591. 9.10 Experiment 9 Sequential Circuits 593. 9.11 Experiment 10 Counters 595. 9.12 Experiment 11 Shift Registers 596. 9.13 Experiment 12 Serial Addition 609.14 Experiment 13 Memory Unit 601. 9.15 Experiment 14 Lamp Handball 603. 9.16 Experiment 15 Clock Pulse Generator 607. 9.17 Experiment 16 Parallel Adder and Accumulator 609. 9.18 Experiment 17 Binary Multiplier 611. 9.19 HDL Simulation Experiments and Rapid Prototyping with FPGAs 615. 10 Standard Graphic Symbols 621. 10.1 Rectangular Shape Symbols 621. 10.2 Qualifying Symbols 624. 10.3 Dependency Notation 626. 10.4 Symbols for Combinational Elements 628. 10.5 Symbols for Flip-flops 630. 10.6 Symbols for Registers 632. 10.7 Symbols for Counters 635. 10.8 Symbol for RAM 637 Appendix 640 Answers to Selected Problems 654 Index 699. Preface. The speed, density, and complexity of today's digital devices are made possible by advances in physical processing technology and digital design methodology. Aside from semiconductor technology, the design of leading-edge devices depends critically on hardware description languages, HDLs, and synthesis tools. 3 public domain languages, Verilog, VHDL, and System Verilog, all play a role in design flows for today's digital devices. HDLs, together with fundamental knowledge of digital logic circuits, provide an entry point to the world of digital design for students majoring in computer science, computer engineering, and electrical engineering. In the not-too-distant past, it would be unthinkable for an electrical engineering student to graduate without having used an oscilloscope. Today, the needs of industry demand that undergraduate students become familiar with the use of at least one hardware description language. Their use of an HDL as a student will better prepare them to be productive members of a design team after they graduate. Given the presence of 3 HDLs in the design arena, we have expanded our presentation of HDLs in digital design to treat Verilog and VHDL, and to provide an introduction to System Verilog. Our intent is not to require students to learn 3 or even 2 languages, but to provide the instructor with a choice between Verilog and VHDL while teaching a systematic methodology for design, regardless of the language, and an optional introduction to System Verilog. Certainly, Verilog and VHDL are widely used and taught, dominate the design space, and have common underlying concepts supporting combinational and sequential logic design. And both are essential to the synthesis of high-density integrated circuits. Our text offers parallel tracks of presentation of both languages, but allows concentration on a single language. The level of treatment of Verilog and VHDL is essentially equal, without emphasizing one language over the other. A language-neutral presentation of digital design is a common thread through the treatment of both languages. A large set of problems, which are stated in language-neutral terms, at the end of each chapter can be worked with either Verilog or VHDL. The emphasis in our presentation is on digital design, with HDLs in a supporting role. Consequently, We present only those details of Verilog, VHDL, and System Verilog that are needed to support our treatment of an introduction to digital design. Moreover, although we present examples using each language, we identify and segregate the treatment of topics and examples so that the instructor can choose a path of presentation for a single language, either Verilog or VHDL. Naturally, a path that emphasizes Verilog can conclude with System Verilog, but it can be skipped without compromising the objectives. The introduction to System Verilog is selective. We present only topics and examples that are extensions of Verilog, and well within the scope of an introductory treatment. To be clear, we are not advocating simultaneous presentation of the languages. The instructor can choose either Verilog/System Verilog or VHDL as the core language supporting an introductory course in digital design. Regardless of the language, our focus is on digital design. The language-based examples throughout the book are not just about the details of an HDL. We emphasize and demonstrate the modeling and verification of digital circuits having specified behavior. Neither Verilog or VHDL are covered in their entirety. Some details of the languages will be left to the reader's continuing education and use of web resources. Regardless of language, our examples introduce a design methodology based on the concept of computer.
Regardless of language, our examples introduce a design methodology based on the
Regardless of language, our examples introduce a design methodology based on the concept of computer-aided modeling of digital systems by means of a mainstream, IEEE standardized hardware description language. This revision of digital design begins each chapter with a statement of its objectives. Problems at the end of each chapter are combined with in-chapter examples and with in-chapter practice exercises. Together, these encounters with the subject matter bring the student closer to achieving the stated objectives and becoming skilled in digital design. Answers are given to selected problems at the end of the book. A solution manual gives detailed solutions to all of the problems at the end of the chapters. The level of detail of the solutions is such that an instructor can use individual problems to support classroom instruction. Multimodal learning. Like the previous editions, this edition of digital design supports a multimodal approach to learning. The so-called VRK1, two-characterization of learning modalities, identifies four major modes by which we learn. 5. Visual, A. Oral, hearing, R. Reading, and K. Kinesthetic. The relatively high level of illustrations and graphical content of our text. 1. Kolb, David A. 2015, 1984. Experiential learning. Experience as the source of learning and development, 2nd edition. Upper Saddle River, New Jersey. Pearson Education. ISBN 9780133892406. OCLC 9098158841. 2. Fleming, Neil D. 2014. The VARK Modalities. vark-learn.com. Addresses the visual V component of VARK. Discussions and numerous examples address the reading R component. Students who exploit the availability of free Verilog, VHDL, and System Verilog simulators and synthesis tools to work assignments are led through a kinesthetic learning experience, including the delight of designing a digital circuit that actually works. The remaining element of VARK, the oral/auditory A experience, depends on the instructor and the attentiveness of the student. Put away the smartphone. We have provided an abundance of materials and examples to support classroom lectures. Thus, a course using digital design can provide a rich, balanced learning experience and address all the modes identified by VARK. For skeptics who might still question the need to present and use HDLs in a first course in digital design, we note that industry does not rely on schematic-based design methods. Schematic entry creates a representation of functionality that is implicit in the constructs and layout of the schematic. Unfortunately, it is difficult for anyone in a reasonably amount of time to determine the functionality represented by the schematic of a logic circuit without having been instrumental in its construction. or without having additional documentation expressing the design intent. Consequently, industry today relies almost exclusively on HDLs to describe the functionality of a design and to serve as a basis for documenting, simulating, testing, and synthesizing the hardware implementation of the design in a standard cell-based ASIC or an FPGA. The utility of a schematic depends on the detailed documentation of a carefully constructed hierarchy of design units. In the past, designers relied on their years of experience to create a schematic of a circuit to implement functionality. Today's designers using HDLs can express functionality directly and explicitly without years of accumulated experience and use synthesis tools to generate the schematic as a byproduct. Automatically, industry adopted HDL-based design flows because schematic entry dooms us to inefficiency, if not failure, in understanding and designing large, complex ICs. Introduction of HDLs in a first course in digital design is not intended to replace fundamental understanding of the building blocks of such circuits, or to eliminate a discussion of manual methods of design. It is still essential for students to understand how hardware works. Thus, this edition of digital design retains a thorough treatment of combinational and sequential logic design and a foundation in Boolean algebra. Manual design practices are presented, and their results are compared with those obtained using HDLs. What we are presenting, however, is an emphasis on how hardware is designed today to better prepare a student for a career in today's industry, where HDL-based design practices are dominant. Flexible at Y. We include both manual and HDL-based design examples. Our end-of-chapter problems cross-reference problems that access a manual design task with a companion problem that uses an HDL to accomplish the assigned task. We also link the manual and HDL-based approaches by presenting annotated results of simulations in the text in answers to selected problems at the end of the text, and extensively in the solution manual. New to this edition. This edition of digital design uses the latest features of IEEE Standard 1364, but only insofar as they support our pedagogical objectives. The revisions and updates to the text include elimination of specialized circuit-level content not typically covered in a first course in logic circuits and digital design, e.g., RTL, DTL, and emitter-coupled logic circuits. Addition of web search topics at the end of each chapter to point students to additional subject matter available on the web. Revision of approximately 1/3 of the problems at the end of the chapters, a solution manual for the entire text, including all new problems. Streamlining of the discussion of Carnot maps. Integration of treatment of basic CMOS technology with treatment of logic gates. Inclusion of an appendix introducing semiconductor technology, treatment of digital design with VHDL, and system Verilog design methodology. A highlight of our presentation is a systematic methodology for designing a state machine to control the data path of a digital system. The framework in which this material is presented treats the realistic situation in which status signals from the data path are used by the controller, i.e., the system has feedback. Thus, our treatment provides a foundation for designing complex and interactive digital systems. Although it is presented with an emphasis on HDL-based design, the methodology is also applicable to manual-based approaches to design and is language neutral. Just enough HDL. We present only those elements of Verilog, VHDL, and system Verilog that are matched to the level and scope of this text. Also, correct syntax does not guarantee that a model meets a functional specification or that it can be synthesized into physical hardware. So, we introduce students to a disciplined use of industry-based practices for writing models to ensure that a behavioral description can be synthesized into physical hardware, and that the behavior of the synthesized circuit will match that of the behavioral description. Failure to follow this discipline can lead to software race conditions in the HDL models of such machines, race conditions in the test bench used to verify them, and a mismatch between the results of simulating a behavioral model and its synthesized physical counterpart. Similarly, failure to abide by industry practices may lead to designs that simulate correctly, but which have hardware latches that are introduced into the design accidentally as a consequence of the modeling style used by the designer. The industry-based methodology we present leads to race-free and latch-free designs. It is important that students learn and follow industry practices in using HDL models, independent of whether a student's curriculum has access to synthesis tools. Verification. In industry, significant effort is expended to verify that the functionality of a circuit is correct. Yet not much attention is given to verification in introductory texts on digital design, where the focus is on design itself, and testing is perhaps viewed as a secondary undertaking. Our experience is that this view can lead to premature high fives and declarations that the circuit works beautifully. Likewise, industry gains repeated returns on its investment in an HDL model by ensuring that it is readable, portable, and reusable. We demonstrate naming practices and the use of parameters to facilitate reusability and portability. We also provide test benches for all of the solutions and exercises to 1. Verify the functionality of the circuit, 2. Underscore the importance of thorough testing, and 3. Introduce students to important concepts such as self-checking test benches. Advocating and illustrating the development of a test plan to guide the development of a test bench, we introduce test plans, albeit simply, in the text and expand them in the solutions manual and in the answers to selected problems at the end of the text. HDL content. We have ensured that all examples in the text and all answers in the solution manual conform to accepted industry practices for modeling digital hardware. As in the previous edition, HDL material is inserted in separate sections so that it can be covered or skipped as desired, does not diminish treatment of manual-based design, and does not dictate the sequence of presentation. The treatment is at a level suitable for beginning students who are learning digital circuits and in HDL at the same time. The text prepares students to work on significant independent design projects and to succeed in a later course in computer architecture and advanced digital design. Instructor resources. Instructors can obtain the following classroom-ready resources from the publisher: a source code and test benches for all Verilog HDL examples in the test, all figures and tables in the text. Source code for all HDL models in the Solutions Manual, a downloadable solutions manual with graphics suitable for classroom presentation HDL simulators. 2 free simulators can be downloaded from www.syncad.com. The first simulator is Verilogger Pro, a traditional Verilog simulator that can be used to simulate the HDL examples in the book and to verify the solutions of HDL problems. This simulator accepts the syntax of the IEEE 1995 standard and will be useful to those who have legacy models. As an interactive simulator, Verilogger Extreme accepts the syntax of IEEE 2001 as well as IEEE 1995, allowing the designer to simulate and analyze design. Ideas before a complete simulation model or schematic is available. This technology is particularly useful for students because they can quickly enter Boolean and D flip-flop or latch input equations to check equivalency or to experiment with flip-flops and latch. Designs. Free design tools that support design entry, simulation, and synthesis of FPGAs are available from www.altera.com and from www.xilinx.com. Chapter Summary. The following is a brief summary of the topics that are covered in each chapter. Chapter 1 presents the various binary systems suitable for representing information in digital systems. The binary number system is explained and binary codes are illustrated. Examples are given for addition and subtraction of signed binary numbers and decimal numbers in binary coded decimal (BCD) format. Chapter 2 introduces the basic postulates of Boolean algebra and shows the correlation between Boolean expressions and their corresponding logic diagrams. All possible logic operations for 2 variables are investigated, and the most useful logic gates used in the design of digital systems are identified. This chapter also introduces basic CMOS logic gates. Chapter 3 covers the map method for simplifying Boolean expressions. The map method is also used to simplify digital circuits constructed with AND/OR, NAND, or NOR gates. All other possible two-level gate circuits are considered, and their method of implementation is explained. Verilog and VHDL are introduced together with simple examples of gate-level models. Chapter 4 outlines the formal procedures for the analysis and design of combinational circuits. Some basic components used in the design of digital systems, such as adders and code converters, are introduced as design examples. Frequently used digital logic functions such as parallel adders and subtractors, decoders, encoders, and multiplexers are explained, and their use in the design of combinational circuits is illustrated. HDL examples are given in gate level, data flow, and behavioral models to show the alternative ways available for describing combinational circuits in Verilog and VHDL. The procedure for writing a simple test bench to provide stimulus to an HDL design is presented. Chapter 5 outlines the formal procedures for analyzing and designing clocked, synchronous, sequential circuits. The gate structure of several types of flip-flops is presented together with a discussion on the difference between level and edge triggering. Specific examples are used to show the derivation of the state table and state diagram when analyzing a sequential circuit. A number of design examples are presented with emphasis in sequential circuits that use D-type flip-flops. Behavioral modeling in Verilog and VHDL for sequential circuits is explained. HDL examples are given to illustrate Mealy and Moore models of sequential circuits. Chapter 6 deals with various sequential circuit components such as registers, shift registers, and counters. These digital components are the basic building blocks from which more complex digital systems are constructed. HDL descriptions of shift registers and counters are presented. Chapter 7 introduces random access memory, RAM, and programmable logic devices. Memory decoding and error correction schemes are discussed. Combinational and sequential programmable devices such as ROMs, PLAs, PALs, CPLDs, and FPGAs are presented. Chapter 8 deals with the register transfer level, RTL, representation of digital systems. The algorithmic state machine, ASM, chart is introduced. A number of examples demonstrate the use of the ASM chart, ASMD chart, RTL representation, and HDL description in the design of digital systems. The design of a finite state machine to control a data path is presented in detail, including the realistic situation in which status signals from the data path are used by the state machine that controls it. This chapter provides the student with a systematic approach to more advanced design projects. Chapter 9 presents experiments that can be performed in the laboratory with hardware that is readily available commercially. The operation of the ICs used in the experiments is explained by referring to diagrams of similar components introduced in previous chapters. Each experiment is presented informally, and the student is expected to design the circuit and formulate a procedure for checking its operation in the laboratory. The lab experiments can be used in a standalone manner too, and can be accomplished by a traditional approach with a breadboard and TTL circuits, or with an HDL/synthesis approach using FPGAs. Today, software for synthesizing an HDL model and implementing a circuit with an FPGA is available at no cost from vendors of FPGAs, allowing students to conduct a significant amount of work in their personal environment before using prototyping boards and other resources in a lab. Circuit boards for rapid prototyping circuits with FPGAs are available at a nominal cost and typically include push buttons, switches, 7-segment displays, LCDs, keypads, and other I/O devices. With these resources, students can work prescribed lab exercises or their own projects and get results immediately. Chapter 10 presents the standard graphic symbols for logic functions recommended by an ENSI/IEEE standard. These graphic symbols have been developed for small-scale integration, SSI, and medium-scale integration, MSI, components, so that the user can recognize each function from the unique graphic symbol assigned. The chapter shows the standard graphic symbols of the ICs used in the laboratory experiments. Acknowledgements: we are grateful to the reviewers of Digital Design, 6E. Their expertise, careful reviews, and suggestions helped shape this edition. Vijay Matasetti, Georgia Tech Dmitry Donetsky, SUNY Stony Brook David Potter, Northeastern Xiaolong Wu, California State Long Beach Avinash Cody, Ohio University Lee Belfour, Old Dominion University. We also wish to express our gratitude to the editorial and publication team at Pearson Education for supporting this edition of our text. We are grateful, too, for the ongoing support and encouragement of our wives, Sandra and Geraldine M. Morris Mano, Emeritus Professor of Computer Engineering, California State University, Los Angeles. Michael D. Ciletti, Emeritus Professor of Electrical and Computer Engineering, University of Colorado at Colorado Springs. Acknowledgements for the Global Edition. Pearson would like to thank and acknowledge the following people for their contributions to this Global Edition. Contributors: Mamita Mitra Manna, Bangabasi College Reviewers. Debaprasad Das, Assam University Nikol Marawala, University Institute of Engineering and Technology, Kampur Tapas Kumar Saha, National Institute of Technology, Durgapur. Chapter 1: Digital Systems and Binary Numbers. Chapter Objectives 1. Understand binary number system. 2. Know how to convert between binary, octal, decimal, and hexadecimal numbers. 3. Know how to take the complement and reduced radix complement of a number. 4. Know how to form the code of a number. 5. Know how to form the parity bit of a word. 1.1 Digital Systems. Digital systems have such a prominent role in everyday life that we refer to the present technological period as the digital age. Digital systems are used in communication, business transactions, traffic control, spacecraft guidance, medical treatment, weather monitoring, the internet, and many other commercial, industrial, and scientific enterprises. That we have digital telephones, digital televisions, digital versatile discs, DVDs, digital cameras, personal, handheld, touchscreen devices, and, of course, digital computers. We enjoy music downloaded to our portable media player, e.g., iPod Touch and other handheld devices having high-resolution displays and touchscreen graphical user interfaces, GUIs. GUIs enable them to execute commands that appear to the user to be simple, but which, in fact, involve precise execution of a sequence of complex internal instructions. Most, if not all, of these devices have a special-purpose digital computer, or processor, embedded within them. The most striking property of the digital computer is its generality. It can follow a sequence of instructions, called a program, which operates in given data. The user can specify and change the program or the data according to the specific need. Because of this flexibility, general-purpose digital computers can perform a variety of information processing tasks that range over a wide spectrum of applications and provide unprecedented access to massive repositories of information and media. One characteristic of digital systems is their ability to represent and manipulate discrete elements of information. Any set that is restricted to a finite number of elements contains discrete information. Examples of discrete sets are the 10 decimal digits, the 26 letters of the alphabet, the 52 playing cards, and the 64 squares of a chessboard. Early digital computers were used for numeric computations. In this case, the discrete elements were the digits. From this application, the term digital computer emerged. Discrete elements of information are represented in a digital system by physical quantities called signals. Electrical signals such as voltages and currents are the most common. Electronic devices called transistors predominate in the circuitry that implement, represent, and manipulate these signals. The signals in most present-day electronic digital systems use just two discrete values and are therefore said to be binary. A binary digit, called a bit, has two numerical values, 0 and 1. Discrete elements of information are represented with groups of bits called binary codes. For example, the decimal digits 0 through 9 are represented in a digital system with a code of 4 bits, e.g., the number 7 is represented by 0111. How a pattern of bits is interpreted as a number depends on the code system in which it resides. To make this distinction, we could write 0111 2 to indicate that the pattern 0111 is to be interpreted in a binary system, and 0111, 10 to indicate that the reference system is decimal. Then 01112 equals 710, which is not the same as 01110, or 111. The subscript indicating the base for interpreting a pattern of bits will be used only when clarification is needed. Through various techniques, groups of bits can be made to represent discrete symbols, not necessarily numbers, which are then used to develop the system in a digital format. Thus, a digital system is a system that manipulates discrete elements of information represented internally in binary form. In today's technology, binary systems are most practical because, as we will see, they can be implemented with electronic components. Discrete quantities of information either emerge from the nature of the data being processed or may be quantized from a continuous process. On the one hand, a payroll schedule is an inherently discrete process that contains employee names, social security numbers, weekly salaries, income taxes, and so on. An employee's paycheck is processed by means of discrete data values such as letters of the alphabet, names, digits, salary, and special symbols such as $. On the other hand, a research scientist may observe a continuous process, e.g., temperature, but record only specific quantities in tabular form. The scientist is thus quantizing continuous data, making each number in the table a discrete quantity. In many cases, the quantization of a process can be performed automatically in analog-to-digital converter, a device that forms a digital, discrete, representation of an analog, continuous, quantity. Digital cameras rely on this technology to quantify the measurements of exposure captured from an image. The general-purpose digital computer is the best-known example of a digital system. The major parts of a computer are a memory unit, a central processing unit, and input-output units. The memory unit stores programs as well as input, output, and intermediate data. The central processing unit performs arithmetic and other data processing operations as specified by the program. The program and data prepared by a user are transferred into memory by means of an input device, such as a keyboard or a touchscreen video display. An output device, such as a printer, receives the results of the computations, and the printed results are presented to the user. A digital computer can accommodate many input and output devices. One very useful device is a communication unit that provides interaction with other users through the internet. A digital computer is a powerful instrument that can perform not only arithmetic computations, but also logical operations. In addition, it can be programmed to make decisions based on internal and external conditions. There are fundamental reasons that commercial products are made with digital circuits. Like a digital computer, most digital devices are programmable. By changing the program in a programmable device, the same underlying hardware can be used for many different applications, thereby allowing its cost of development to be spread across sales to a wider customer base. Dramatic cost reductions in digital devices have come about because of advances in digital integrated circuit technology. As the number of transistors that can be put on a piece of silicon increases to produce complex functions, the cost per unit decreases, and digital devices can be bought at an increasingly reduced price. Equipment built with digital integrated circuits can perform at a speed of hundreds of millions of operations per second. Digital systems can be made to operate with extreme reliability by using error-correcting codes. An example of this strategy is the Digital Versatile Disc, DVD, in which digital information representing photos, video, audio, and other data is recorded without the loss of a single item. Digital information on a DVD is recorded in such a way that, by examining the code in each digital sample before it is played back, any error can be automatically identified and corrected. A digital system is an interconnection of digital modules. To understand the operation of each digital module, it is necessary to have a basic knowledge of digital circuits and their logical function. The first 7 chapters of this book present the basic tools of digital design, such as logic gate structures, combinational and sequential circuits, and programmable logic devices. Chapter 8 introduces digital design at the register transfer level, RTL, using a modern, public domain hardware description language, HDL. Chapter 9 concludes the text with laboratory exercises using digital circuits. Today's array of inexpensive digital devices is made possible by the convergence of fabrication technology and computer-based design methodology. Today's best practice in digital design methodology uses HDLs to describe and simulate the functionality of a digital circuit. An HDL resembles a programming language and is suitable for describing digital circuits in textual form. It is used to simulate a digital system to verify its operation before hardware is built. It is also used in conjunction with logic synthesis tools to automate the design process. Because it is important that students become familiar with an HDL-based design methodology, HDL descriptions of digital circuits are presented throughout the book. While these examples help illustrate the features of an HDL, they also demonstrate the best practices used by industry to exploit HDLs. Ignorance of these practices will lead to cute, but worthless, HDL models that may simulate a phenomenon but that cannot be synthesized by design tools, or to models which waste silicon area or synthesize to hardware that does not operate correctly. As previously stated, digital systems manipulate discrete quantities of information that are represented in binary form. Operands used for calculations may be expressed in the binary number system. Other discrete elements, including the decimal digits and characters of the alphabet, are represented in binary codes. Digital circuits, also referred to as logic circuits, process data by means of binary logic elements, logic gates, using binary signals. Quantities are stored in binary, two-valued storage elements, flip-flops. The purpose of this chapter is to introduce the various binary concepts and provide a foundation for further study in the succeeding chapters. 1.2. Binary numbers. A decimal number such as 7,392 represents a quantity equal to 7 thousands, plus 3 hundreds, plus 9 tens, plus 2 units. The thousands, hundreds, etc. are powers of 10 implied by the position of the coefficients, symbols, in the number. To be more exact, 7,392 is a shorthand notation for what should be written as plus 7 by 1033 by 1029 by 1012 by 100. However, the convention is to write only the numeric coefficients and, from their position, deduce the necessary powers of 10, with powers increasing from right to left. In general, a number with a decimal point is represented by a series of coefficients, A5, A4, A3, A2, A1, A0, a minus 1, a minus 2, a minus 3. The coefficients aj are any of the 10 digits, 0, 1, 2, 9, and the subscript value j gives the place value and, hence, the power of 10 by which the coefficient must be multiplied. Thus, the preceding decimal number can be expressed as 105A5 plus 104A4 plus 103A3 plus 102A2 plus 101A1 plus 100A0 plus 10 minus 1 a minus 1 plus 10 minus 2 a minus 2 plus 10 minus 3 a minus 3. With A3 equals 7, A2 equals 3, A1 equals 9, and A0 equals 2, and the other coefficients equal to 0. The radix of a number system determines the number of distinct values that can be used to represent any arbitrary number. The decimal number system is said to be of base, or radix, 10 because it uses 10 digits and the coefficients are multiplied by powers of 10. The binary system is a different number system. The coefficients of the binary number system have only two possible values, 0 and 1. Each coefficient aj is multiplied by a power of the radix, for example, 2j, and the results are added to obtain the decimal equivalent of the number. The radix point, e.g., the decimal point when 10 is the radix, distinguishes positive powers of 10 from negative powers of 10. For example, the decimal equivalent of the binary number 11,010.11 is 26.75, as shown from the multiplication of the coefficients by powers of 2 to 2. 24 plus 23 plus 22 plus 21 plus 20 plus 2 to 1 plus 1 by 1 asterisk 0 asterisk 1 asterisk 0 asterisk 1 by 1 asterisk equals 26.75. There are many different number systems. In general, a number expressed in a base R system has coefficients multiplied by powers of R. Hashtag RN1 hashtag RN hashtag R2 hashtag R hashtag plus 1 plus plus R1. G plus and in A2 A1 plus A0 plus A1. Hashtag R2 plus RM G plus plus A2 yem. The coefficients AJ range in value from 0 to R1. To distinguish between numbers of different bases, we enclose the coefficients in parentheses and write a subscript equal to the base used, except sometimes for decimal numbers, where the content makes it obvious that the base is decimal. An example of a base 5 number is 53 plus 52 plus 51 plus 50 plus 5 to 1 for 1021.2. 5 equals 4 asterisk 0 asterisk 2 by 1 by 2 asterisk equals 511.4. 10. The coefficient values for base 5 can be only 0, 1, 2, 3, and 4. The octal number system is a base 8 system that has 8 digits 0, 1, 2, 3, 4, 5, 6, 7. An example of an octal number is 127.4. 8. To determine its equivalent decimal value, we expand the number in a power series with a base of 8. 82 plus 81 plus 80 plus 8 to 1, 127.4. 8 is equal to 1 times 2 times 7 asterisk 4 asterisk equals 87.5. 10. Note that the digits 8 and 9 cannot appear in an octal number. It is customary to borrow the needed R digits for the coefficients from the decimal system when the base of the number is less than 10. The letters of the alphabet are used to supplement the 10 decimal digits when the base of the number is greater than 10. For example, in the hexadecimal, base 16 number system, the first 10 digits are borrowed from the decimal system. The letters A, B, C, D, E, and F are used for the digits 10, 11, 12, 13, 14, and 15, respectively. An example of a hexadecimal number is +++B65F. 16 is equal to 11 times 163 6 by 162 5 by 161 15 times 160 is equal to 46,687. 10. The hexadecimal system is used commonly by designers to represent long strings of bits in the addresses, instructions, and data in digital systems. For example, B65F is used to represent 1011101100101111. As noted before, the digits in a binary number are called bits. When a bit is equal to 0, it does not contribute to the sum during the conversion. Therefore, the conversion from binary to decimal can be obtained by adding only the numbers with powers of 2 corresponding to the bits that are equal to 1. For example, 110,101. 2 equals 32 plus 16 plus 4 plus 1 equals 53. 10. There are 4 ones in the binary number. The corresponding decimal number is the sum of the 4 powers of 2. 0 and the first 24 numbers obtained from 2 to the power of n are listed in Table 1.1. In computer work, 210 is referred to as K, kilo, 212. 220, 230 as m, mega, as g, giga, and 240 as t, tera. Thus, for k equals 4096 and 224. 16m equals 16,777,216. Computer memory capacity and word size are usually given in bytes. A byte is equal to 8 bits and can accommodate, i.e., represent the code of 1 keyboard character. A computer hard disk with 4 gigabytes of storage has a capacity of 4G equals 232 bytes, approximately 4 billion bytes. A terabyte is 1,024 gigabytes, approximately 1 trillion bytes. Table 1.1 powers of 2, 2, and 2, and 2, n, 0, 1, 8, 256, 16, 65,530, 6, 1, 2, 9, 512, 17, 131,000, and 72, 2, 4, 10, 1,000, and 24, 1k. 18 260 2144 38 11 2048 19 524 288 4 16 12 4096 4K 21,048,576 1M 532 13 8192 21 2,097,152 6 64 14 16,384 22 4,194,304 7 1 28 15 30 2,768 23 8,388,608. Arithmetic operations with numbers in base are follow the same rules as for decimal numbers. When a base other than the familiar base 10 is used, one must be careful to use only the allowable digits. Examples of addition, subtraction, and multiplication of two binary numbers are as follows. Augend 101,101 minuend, 101,101 multiplicand, 1011 addend, plus 100,111 subtrahend, 100,111 multiplier, asterisk 101. Sum 101,0100 difference, 0,00110, 1011, 0,000 partial product, 1011 product, 110111. The sum of two binary numbers is calculated by the same rules as in decimal, except that the digits of the sum in any significant position can be only 0 or 1. Any carry obtained in a given significant position is used by the pair of digits one significant position higher. Subtraction is slightly more complicated. The rules are still the same as in decimal, except that the borrow in a given significant position adds 2 to a minuend digit. A borrow in the decimal system adds 10 to a minuend digit. Multiplication is simple. The multiplier digits are always 1 or 0. Therefore, the partial products are equal either to a shifted, left, copy of the multiplicand or to 0. Practice exercise 1.1. 24 plus 23 plus 22 plus 21 plus 20? What is the decimal value of 1 asterisk 0 asterisk 1 asterisk 0 asterisk 1 asterisk answer? 21 1.3 number, base conversions. Representations of a number in a different radix are said to be equivalent if they have the same decimal representation. For example, 0011, 8 and 1001, 2 are equivalent both. Have decimal value 9. The conversion of a number in base R to decimal is done by expanding the number in a power series and adding all the terms as shown previously. We now present a general procedure for the reverse operation of converting a decimal number to a number in base R. If the number includes a radix point, it is necessary to separate the number into an integer part and a fraction part, since each part must be converted differently. The conversion of a decimal integer to a number in base R is done by dividing the number and all successive quotients by R and accumulating the remainders. This procedure is best illustrated by example. Example 1.1. Convert decimal 41 to binary. First, 41 is divided by 2 to give an integer quotient of 20 and a remainder of 12. Then the quotient is again divided by 2 to give a new quotient and remainder. The process is continued until the integer quotient becomes 0. The coefficients of the desired binary number are obtained from the remainders as follows. Integer remainder coefficient quotient equals 20 plus A0 112 is equal to 41, 2 equals 10 plus 0, A10 equals 5 plus 0, A2 equals 0, 20 greater than 2, 10 greater than 2, 12 is equal to 2 plus A3 equals 1 is equal to 1 plus 0, A4 equals 0 is equal to 0 plus 1, A5 12 is equal to 5, 2 2 greater than 2, 1 greater than 2. Therefore, the answer is 41 10 equals A5 A4 A3 A2 A1 A0, 2 equals 101,001 2. The arithmetic process can be manipulated more conveniently as follows. Integer 4 1 20 10 5 2 1 0, remainder 1 0 0 1 0 1 101,000 and 1 equals answer. Conversion from decimal integers to any base or system is similar to this example, except that division is done by r instead of 2. Example 1.2. Convert decimal 153 to octal. The required base r is 8. First, 153 is divided by 8 to give an integer quotient of 19 and a remainder of 1. Then 19 is divided by 8 to give an integer quotient of 2 and a remainder of 3. Finally, 2 is divided by 8 to give a quotient of 0 and a remainder of 2. This process can be conveniently tabulated as follows. 153 19 1 2 3 0 2 equals 231 8. The conversion of a decimal fraction to binary is accomplished by a method similar that used for integers. However, multiplication is used instead of division, and integers instead of remainders are accumulated. Again, the method is best explained by example. Example 1.3. Convert 0.6875 10 to binary. First, 0.6875 is multiplied by 2 to give an integer and a fraction. Then the new fraction is multiplied by 2 to give a new integer and a new fraction. The process is continued until the fraction becomes 0 or until the number of digits has sufficient accuracy. The coefficients of the binary number are obtained from the integers as follows. Integer fraction coefficient. 0.6875 times 2 is equal to 1 plus 0.3750 a. 1 equals 1 0.3750 times 2 is equal to 0 plus 0.7500 a. 2 equals 0.7500 times 2 is equal to 1 plus 0.5000 a. 3 equals 1 0.5000 times 2 is equal to 1 plus 0.0000 a. 4 equals 1. Therefore, the answer is 0.6875. 10 equals 0. A1a, 2a, 3a, 4. 2 equals 0.10112. To convert a decimal fraction to a number expressed in base r, a similar procedure is used. However, multiplication is by r instead of 2, and the coefficients found from the integers may range in value from 0 to r, 1 instead of 0 and 1. Example 1.4 Convert 0.513 10 to octal. 0.513 times 8 is equal to 4.1040. 0.104 times 8 is equal to 0.832. 0.832 times 8 is equal to 6.656. 0.656 times 8 is equal to 5.248. 0.248 times 8 is equal to 1.984. 0.984 times 8 is equal to 7.872. The answer, to 6 significant figures, is obtained from the integer part of the products. 0.513, 10 equals 0.406517c. 8. The conversion of decimal numbers with both integer and fraction parts is done by converting the integer and the fraction separately and then combining the two answers. Using the results of examples 1.1 and 1.3, we obtain 41.6875, 10 equals 101, 001, 1011. 2 from examples 1.2 and 1.4, we have 153.513, 10 equals 231.406517. 8. Practice exercise 1.2. Convert 117.23, 10 to octal. Answer: 117.23, 10 equals 165.1656, 8. 1.4 Octal and hexadecimal numbers. The conversion from and to binary, octal, and hexadecimal plays an important role in digital computers. Because shorter patterns of hex characters are easier to recognize than long patterns of ones and zeros. Since 23 is equal to 8 and 24 is equal to 16, each octal digit corresponds to 3 binary digits and each hexadecimal digit corresponds to 4 binary digits. The first 16 numbers in the decimal, binary, octal, and hexadecimal number systems are listed in Table 1.2. The conversion from binary to octal is easily accomplished by partitioning the binary number into groups of 3 digits each, starting from the binary point and proceeding. Table 1.2 numbers with different bases: decimal, binary, octal, hexadecimal, base 10, base 2, base 8, base 16. 0 0 0 0 0 0 0 0 0 0 1 0 0 0 1 0 1 1 0 2 0 0 1 0 0 2 2 0 3 0 0 1 1 0 3 3 0 4 0 100 0 4 4 0 5 0 1 0 1 0 5 5 0 6 0 1 1 0 0 6 6 0 7 0 1 1 1 0 7 7 0 8 1000 10 8 0 9 1000 1 11 9 10 1000 10 12 A 11 1000 11 13 B 12 1100 14 C 13 11 01 15 D 14 11 10 16 E 15 11 11 17 F. To the left and to the right. The corresponding octal digit is then assigned to each group. The following example illustrates the procedure. 10,110,000,1,100 number 111 100 million 110 226153740 equals 26,153.7406. A conversion from binary to hexadecimal is similar, except that the binary number is divided into groups of 4 digits. 10 1 100 0 1 1 0 1 0 1 1 number 11 11 0 0 1 0 2 2 C 6 B F 2 equals 2 C 6 B to F 2 16. The corresponding hexadecimal or octal digit for each group of binary digits is easily remembered from the values listed in Table 1.2. Conversion from octal or hexadecimal to binary is done by reversing the preceding procedure. Each octal digit is converted to its 3-digit binary equivalent. Similarly, each hexadecimal digit is converted to its 4-digit binary equivalent. The procedure is illustrated in the following examples. 673.124, 8 equals 110 6 111 70 11 3 number 0 0 1 1 0 10 2 100 2 4 and 306 D 16 equals 0 0 1 1 3 0 0 0 0 0 0 1 1 0 6 number 1101 2D. Binary numbers are difficult to work with because they require 3 or 4 times as many digits as their decimal equivalents. For example, the binary number 111111111 1111 is equivalent to decimal 4095. However, digital computers use binary representation of numbers, and it is sometimes necessary for the human operator or user to communicate directly with the machine by means of such numbers. One scheme that retains the binary system in the computer, but reduces the number of digits the human must consider. One utilizes the relationship between the binary number system and the octal or hexadecimal system. By this method, the human thinks in terms of octal or hexadecimal numbers and performs the required conversion by inspection when direct communication with the machine is necessary. Thus, the binary number 11111111 has 12 digits and is expressed in octal as 7,777, 4 digits, or in hexadecimal as FFF, 3 digits. During communication between people about binary numbers in the computer, the octal or hexadecimal representation is more desirable because it can be expressed more compactly with a third or a quarter of the number of digits required for the equivalent binary number. Thus, most computer manuals use either octal or hexadecimal numbers to specify instructions and other binary quantities. The choice between them is arbitrary, although hexadecimal tends to win out since it can represent a byte with 2 digits. Practice exercise 1.3. Find the binary representation of 13,510. Answer: 13,510 is equal to 1,110,000,1. 2. Practice exercise 1.4. Find the octal representation of 135. 10. Answer: 13,510 is equal to 7,028 1.5 complements of numbers. Complements are used in digital computers to simplify the subtraction operation and for logical manipulation. Simplifying operations leads to simpler, less expensive circuits to implement the operations. There are two types of complements for each base R system, the radix complement and the diminished radix complement. The first is referred to as the R's complement and the second as the R1 ES complement. When the value of the base R is substituted in the name, the two types are referred to as the 2's complement and 1's complement for binary numbers and the 10's complement and 9's complement for decimal numbers. One machines having a word length of 64 bits are common. Diminished radix complement given a number n in base are having n digits, the R1 ES complement of n, that is 12, its diminished radix complement is defined as 1 RNN. For decimal numbers, R equals 10 and R1 is equal to 9, so the 9's complement of n is 110 n minus 12 minus n. In this case, 10n represents a number that consists of a single 1 followed by n zeros. 10n 1 is a number represented by n nines. For example, if n equals 4, we have 104 is equal to 10,000 and 104 minus 1 is equal to 9,999. It follows that the 9's complement of a decimal number is obtained by subtracting each digit from 9. Here are some numerical examples. The 9's complement of 546,700 is 999,999. 546,700 is equal to 453,299. The 9's complement of 0,12398 is 999,999. 0,12398 equals 987,601. 2n for binary numbers R equals 2 and R1 is equal to 1, so the 1's complement of n is 1. n. Again, 2n is represented by a binary number that consists of a 1 followed by n zeros. 2n 1 is a binary number represented by n ones. For example, if n equals 4, we have 24 equals 10,000, 2 and 24 to 1 equals 1111, 2. Thus, the 1's complement of a binary number is obtained by subtracting each digit from 1. However, when subtracting binary digits from 1, we can have either 1 minus 0 is equal to 1 or 1 minus 1 is equal to 0, which causes the bit to change from 0 to 1 or from 1 to 0, respectively. Therefore, the 1's complement of a binary number is formed by changing 1's to 0's and 0's to 1's. The following are some numerical examples. The 1's complement of 101, 1000 is 010, 0111. The 1's complement of 010, 1101 is 101, 0010. The R1 US complement of octal or hexadecimal numbers is obtained by subtracting each digit from 7 or F, decimal 15, respectively. Radix complement. The R's complement of an n-digit number n in base R is defined as Rn, n for n0 and as 0 for n equals 0. Comparing with the R1 ES complement, we note that the R's complement is obtained by adding 1 to the R1 ES complement, since Rn and equals Rn1 and plus 1. Thus, the 10's complement of decimal 2,389 is 7,610 plus 1 is equal to 7,611 and is obtained by adding 1 to the 9's complement value. The 2's complement of binary 100,100 is 0,100, 11 plus 1 equals 0,10100 and is obtained by adding 1 to the 1's complement value. Since 10 is a number represented by a 1 followed by n zeros, 10 n, which is the 10's complement of n, can be formed also by leaving all least significant zeros unchanged. Subtracting the first non-zero least significant digit from 10 and subtracting all higher significant digits from 9. Thus, the The 10's complement of 0,12398 is 987,602 and the 10's complement of 246,700 is 753,300. The tens complement of the first number, 0,12398, is obtained by subtracting 8 from 10 in the least significant position and subtracting all other digits from 9. The 10's complement of the second number, 246700, is obtained by leaving the two least significant zeros unchanged, subtracting 7 from 10, and subtracting the other three digits from 9. Practice exercise 1.5. Find A. The diminished radix, 9's, complement, and B. The radix, 10's, complement of 13,510. Answer. A. 9's complement, 86,410. B. 10's complement, 86510. Similarly, the 2's complement can be formed by leaving all least significant zeros and the first one unchanged, and replacing ones with zeros and zeros with ones in all other higher significant digits. For example, the 2's complement of 110, 1100 is 001, 0100, and the 2's complement of 011, 0111 is 100, 1001. The 2's complement of the first number is obtained by leaving the two least significant zeros and the first one unchanged, and then replacing ones with zeros and zeros with ones in the other foremost significant digits. The 2's complement of the second number is obtained by leaving the least significant one unchanged and complementing all other digits. In the previous definitions, it was assumed that the numbers did not have a radix point. If the original number n contains a radix point, the point should be removed temporarily in order to form the r's or r1's complement. The radix point is then restored to the complemented number in the same relative position. It is also worth mentioning that the complement of the complement restores the number to its original value. To see this relationship, note that the r's complement of n is rn, n, so that the complement of the complement is rn1 rnn2 equals n and is equal to the original number. Subtraction with complements. The direct method of subtraction taught in elementary schools uses the borrow concept. In this method, we borrow a 1 from a higher significant position when the minuend digit is smaller than the subtrahend digit. The method works well when people perform subtraction with paper and pencil. However, when subtraction is implemented with digital hardware, the method is less efficient than the method that uses complements. The subtraction of two n-digit and sign numbers m, n and base r can be done as follows. 1. Add the minuend m to the r's complement of the subtrahend n, mathematically, and 2 equals rn. m plus 1 rnm, n plus rn. 2. If mun, the sum will produce an end carry which can be discarded. What is left is the result m, n.
N3.
If n, the sum does not produce an end carry and is equal to rn, m6m, which is the r's complement of n, m. To obtain the answer in a familiar form, take the r's complement of the sum and place a negative sign in front. The following examples illustrate the procedure. Example 1.5. Using 10's complement, subtract 72,532 to 3,250. M equals 72,532. 10's complement of n equals plus 96,750. Sum equals 169,282. Discard and carry 105 equals 100,000. Answer equals 69,282. Note that m has 5 digits and n has only 4 digits. Both numbers must have the same number of digits, so we write n as 03250. Taking the 10's complement of n produces a 9 in the most significant position. The occurrence of the end carry signifies that mun and that the result is therefore positive. Example 1.6. Using 10's complement, subtract 3,250 to 72,532. m equals 0, 3, 2, 5, 0, 10 es complement of n equals plus 27,468 sum equals 30,718. There is no end carry. Therefore, the answer is written with a minus sign as dash 10's complement of 30718 equals 69282. Note that since 3256.72532, the result is negative. Because we are dealing with unsigned numbers, there is really no way to get an unsigned result for this case. When subtracting with complements, we recognize the negative answer from the absence of the end carry and the complemented result. When working with paper and pencil, we can change the answer to a signed negative number in order to put it in a familiar form. Subtraction with complements is done with binary numbers in a similar manner, using the procedure outlined previously. Example 1.7. Given the two binary numbers x equals 101, 0100 and y equals 100, 0011, perform the subtraction a, x, y and b, y, x by using 2's complements. A, x equals 101, 01002, s complement of y equals plus 011, 1101 sum equals 100100001 discard and carry 27 to 10 million equals answer. X, y equals 001, 0001 b, y equals 100, 00112, s complement of x equals plus 010, 1100 sum equals 110, 1111. There is no end carry. Therefore, the answer is y. X equals dash 2 s complement of 110, 1111 equals 001, 0001. Subtraction of unsigned numbers can also be done by means of the R1's complement. Remember that the R1 es complement is 1 less than the R's complement. Because of this, the result of adding the minuend to the complement of the subtrahend produces a sum that is 1 less than the correct difference when an end carry occurs. Removing the end carry and adding 1 to the sum is referred to as an end-around carry. Example 1.8. Repeat example 1.7, but this time using 1's complement. A, x, y equals 101, 0100, 100, 0011 x equals 1 es complement of y equals sum equals end at around carry equals answer. X, y equals b, y, x equals 100, 0011, 101, 0100 y equals 1 es complement of x equals sum equals 101, 0100 plus 011, 1100100000 plus 1001, 0001. 100, 0011 plus 010, 101110, 1110. There is no end carry. Therefore, the answer is y. X equals dash 1 es complement of 110, 1110 equals 001, 0001. Note that the negative result is obtained by taking the 1's complement of the sum, since this is the type of complement used. The procedure with end-around carry is also applicable to subtracting unsigned decimal numbers with 9's complement. Practice exercise 1.6. Given x equals 110, 1010, 2 and y equals 010, 10112, a, find x, y and b, find y, x using 2's complements. Answer, a, x igual a 110, 1010, 2 igual a 10.610, igual a 010, 1011, 2 igual a 4.310x, igual a 10.610 a 43.100.000.
Given x equals 110, 101.
Given x equals 110, 1010, 2 and y equals 010, 10112, a, find x, y and b, find y, x using 2's complements. Answer, a, X igual a 1, 10, 10, 10, 2 igual a 10.610, y igual a 0, 10, 10, 11, 2 igual a 4.310x, y igual a 10.610 a 43.106.310. 2's complement of y, 1, 0, 1, 0, 1, 0, 1, 2x, y equals 1, 1, 0, 1, 0, 1, 0, 2 plus 1, 0, 1, 0, 1, 0, 1, 2 equals 0, 1, 1, 1, 1, 1, 1, 2 equals 6,310. B, y, x equals 4,310, 1, 0, 6, 1, 0, 6310 equals 2's complement of x, 1, 0, 0, 1, 0, 1, 1, 0, 2y, x equals 0, 1, 0, 1, 0, 1, 1, 2 plus 0, 0, 1, 0, 1, 1, 0, 2 equals 1, 0, 0, 0, 0, 0, 1, 2 no and carry y, x equals 2's complement of 1, 0, 0, 0, 0, 0, 1, 2y, x equals dash 0, 1, 1, 1, 1, 1, 1, 2 equals 6310. Practice exercise 1.7. Repeat practice exercise 1.5 using 1's complements. Answer. A, x equals 1, 1, 0, 1, 0, 1, 0, 2 equals 10,610, y equals 0, 1, 0, 1, 0, 1, 1, 2 equals 4,310x, y equals 10,610, 4310 to 6310. 1's complement of y, 1, 0, 1, 0, 1, 0, 0, 2x, y equals 1, 1, 0, 1, 0, 1, 0, 2. Plus 1, 0, 1, 0, 1, 0, 0, 2, 1, 0, 1, 1, 1, 1, 1, 0, 2 and at around carry x, y equals 0, 1, 1, 1, 1, 1, 0, 2 plus 0, 0, 0, 0, 0, 0, 1, 2 equals 0, 1, 1, 1, 1, 1, 1, 2 equals 6,310. B, x equals 1, 1, 0, 1, 0, 1, 0, 2 equals 10,610, y equals 0, 1, 0, 1, 0, 1, 1, 2 equals 4,310 y, x equals 4,310, 10,610 equals 6,310. 1's complement of x, 0, 0, 1, 0, 1, 0, 1, 2y, x equals 0, 1, 0, 0, 0, 1, 1, 2 plus 0, 0, 1, 0, 1, 0, 1, 2. 0, 1, 1, 1, 0, 0, 0, 2 no and around carry y, x equals 1's complement of 0, 1, 1, 1, 0, 0, 0, 2 plus 0, 0, 0, 0, 0, 0, 1, 2, y, x equals 1's complement of 1, 0, 0, 0, 0, 0, 1, 2 equals 0, 1, 1, 1, 1, 1, 0, 2 equals 6310. 1.6s Ignd binary numbers. Positive integers, including 0, can be represented as unsigned numbers. However, to represent negative integers, we need a notation for negative values. In ordinary arithmetic, a negative number is indicated by a minus sign and a positive number by a plus sign. Because of hardware limitations, computers must represent everything with binary digits. It is customary to represent the sign with a bit placed in the leftmost position of the number. The convention is to make the sign bit 0 for positive and 1 for negative. It is important to realize that both signed and unsigned binary numbers consist of a string of bits when represented in a computer. The user determines whether the number is signed or unsigned. If the binary number is signed, then the leftmost bit represents the sign, and the rest of the bits represent the number. If the binary number is assumed to be unsigned, then the leftmost bit is the most significant bit of the number. For example, the string of bits 0, 1, 0, 0, 1 can be considered as 9, unsigned binary, or as plus 9, signed binary, because the leftmost bit is 0. The string of bits 1, 1, 0, 0, 1 represents the binary equivalent of 25 when considered as an unsigned number and the binary equivalent of 9 when considered as a signed number. This is because the one that is in the leftmost position designates a negative, and the other 4 bits represent binary 9. Usually, there is no confusion in interpreting the bits if the type of representation for the number is known in advance. Practice exercise 1.8. Which bit of a signed binary number represents the sign? Answer. The leftmost bit. Practice exercise 1.9. What unsigned binary number is represented by the string of bits 11,001? Answer. 2,510. The representation of the sign numbers in the last example is referred to as the sign magnitude convention. In this notation, the number consists of a magnitude and a symbol, plus or a bit, 0 or 1, indicating the sign. This is the representation of signed numbers in ordinary arithmetic. When arithmetic operations are implemented in a computer, it is more convenient to use a different system, referred to as the sign complement system, for representing negative numbers. In this system, a negative number is indicated by its complement. Whereas the sign magnitude system negates a number by changing its sign, the sign complement system negates a number by taking its complement. Since positive numbers always start with 0, plus, in the leftmost position, the complement will always start with a 1, indicating a negative number. The sign complement system can use either the 1's or the 2's complement, but the 2's complement is the most common. As an example, consider the number 9, represented in binary with 8 bits. Plus 9 is represented with a sign bit of 0 in the leftmost position, followed by the binary equivalent of 9, which gives 000001001. Note that all 8 bits must have a value. Therefore, zeros are inserted following the sign bit up to the first one. Although there is only one way to represent plus 9, there are 3 different ways to represent 9 with 8 bits, signed at magnitude representation. 10001001 signed at 1s at complement representation. 11110110 signed at 2s at complement representation. 11110111 Practice exercise 1.10. What decimal number does the sign magnitude binary number n equals 10,011 represent? Answer. N equals 310. Practice exercise 1.11. Convert the sign magnitude binary number n equals 01100 to a negative value having the same magnitude. Answer. N equals 11,100. In sign magnitude, 9 is obtained from plus 9 by changing only the sign bit in the leftmost position from 0 to 1. In signed 1's complement, 9 is obtained by complementing all the bits of plus 9, including the sign bit. The sign 2's complement representation of 9 is obtained by taking the 2's complement of the positive number, including the sign bit. Table 1.3 lists all possible 4-bit signed binary numbers in the 3 representations. The equivalent decimal number is also shown for reference. Note that the positive numbers in all 3 representations are identical and have 0 in the leftmost position. The sign 2's complement system has only one representation for 0, which is always positive. The other 2 systems have either a positive 0 or a negative 0, something not encountered in ordinary arithmetic. Note that all negative numbers have a 1 in the leftmost bit position. That is the way we distinguish them from the positive numbers. With 4 bits, we can represent 16 binary numbers. In the sign magnitude and the 1's complement representations, there are 8 positive numbers and 8 negative numbers, including 2 zeros. In the 2's complement representation, there are 8 positive numbers, including 1 0 and 8 negative numbers. Practice exercise 1.12. Represent 5 3-ways with 8 bits. A. Sign magnitude. B. Signed 1's complement. And C. Signed 2's complement. Answer. A. 10000101. B. 11111010. And C. 11111011. Table 1.3 Signed binary numbers. Signed 2's, signed 1's, signed decimal complement magnitude plus 70111, 0111, 0111 plus 60110, 0110, 0110 plus 50101, 0101, 0101 plus 40100, 0100, 0100 plus 300, 110, 011 plus 2. 001000100010 plus 1000100100001 plus 0000000000000 0 to 1111 1000 to 11111 1110 1001 21110 1101 1010 31101 1100 1011 4100 1011 1100 51011 1010 1101 61010 1001 1110 7 1000 1 1000 1111 to 8 1000. Practice exercise 1.13 in the sign 2's complement system. Negate the number 710, represented with 8 bits. Answer: n equals 00000111121 es comp equals 1111 10,000 and 22 s comp equals 1111 10012. The sign magnitude system is used in ordinary arithmetic, but is awkward when employed in computer arithmetic because of the separate handling of the sign and the magnitude. Therefore, the sign complement system is normally used. The ones complement imposes some difficulties and is seldom used for arithmetic operations. It is useful as a logical operation, since the change of 1 to 0 or 0 to 1 is equivalent to a logical complement operation, as will be shown in the next chapter. The discussion of sign binary arithmetic that follows deals exclusively with the sign 2's complement representation of negative numbers. The same procedures can be applied to the signed 1's complement system by including the end around carry, as is done within sign numbers. Arithmetic addition. The addition of two numbers in the sign magnitude system follows the rules of ordinary arithmetic. If the signs are the same, we add the two magnitudes and give the sum the common sign. If the signs are different, we subtract the smaller magnitude from the larger and give the difference the sign of the larger magnitude. For example, plus 25 plus 37 equals dash 37 to 25 equals 12 is done by subtracting the smaller magnitude 25 from the larger magnitude 37 and appending the sign of 37 to the result. This is a process that requires a comparison of the signs and magnitudes and then performing either addition or subtraction. The same procedure applies to binary numbers in sign magnitude representation. In contrast, the rule for adding numbers in the sign complement system does not require a comparison or subtraction, but only addition. The procedure is very simple and can be stated as follows for binary numbers: the addition of two signed binary numbers with negative numbers represented in sign 2's complement form is obtained from the addition of the two numbers, including their sign bits. A carry out of the sign bit position is discarded. Numerical examples for addition follow: plus 6. 0000110 611111010 plus 1300000110 plus 1300000110 plus 19000010 11 plus 7000000 111 plus 600000110 611111010 1311110011 131111100011 711111001 1911101101. Note that negative numbers must be initially in 2's complement form and that, if the sum obtained after the addition is negative, it is in 2's complement form. For example, 7 is represented as 11111001, which is the 2's complement of plus 7. In each of the four cases, the operation performed is addition with the sign bit included. Any carry out of the sign bit position is discarded, and negative results are automatically in 2's complement form. In order to obtain a correct answer, we must ensure that the result has a sufficient number of bits to accommodate the sum. If we start with two n-bit numbers and the sum occupies n plus 1 bits, we say that an overflow occurs. When one performs the addition with paper and pencil, an overflow is not a problem because we are not limited by the width of the page. We just extend the word by adding another 0 to a positive number or another 1 to a negative number in the most significant position to extend the number to n plus 1 bits, and then perform the addition. Overflow is a problem in computers because the number of bits that hold a number is finite and fixed, and a result that exceeds the finite value by 1 cannot be accommodated. The complement form of representing negative numbers is unfamiliar to those used to the sign magnitude system. To determine the value of a negative number in signed 2's complement, it is necessary to convert the number to a positive number to place it in a more familiar form. For example, the signed binary number 11111001 is negative because the leftmost bit is 1. Its 2's complement is 00000111, which is the binary equivalent of plus 7. We therefore recognize the original negative number to be equal to 7. Arithmetic subtraction of two signed binary numbers when negative numbers are in is simple and can be stated as follows. Take the 2's complement of the subtrahend, including the sign bit, and add it to the minuend, including the sign bit. A carryout of the sign bit position is discarded. This procedure is adopted because a subtraction operation can be changed to. If the sign of the subtrahend is changed, as is demonstrated by a plus b equals a plus b, a b equals a plus b. But changing a positive number to a negative number is easily done by taking the 2's complement of the positive number. The reverse is also true, because the complement of a negative number in complement form produces the equivalent positive number. To see this, consider the subtraction 6, 13 equals plus 7. In binary with 8 bits, this operation is written as 11111010, 11110011. The subtraction is changed to addition by taking the 2's complement of the subtrahend, 13, giving plus 13. In binary, this is 11111010 plus 0000110 equals 100, 000111. Removing the end carry, we obtain the correct answer, 00000111 plus 7. It is worth noting that binary numbers in the sign complement system are added and subtracted by the same basic addition and subtraction rules as in sign numbers. Therefore, computers need only one common hardware circuit to handle both types of arithmetic. This consideration has resulted in the sign complement system being used in virtually all arithmetic units of computer systems. The user or programmer must interpret the results of such addition or subtraction differently, depending on whether it is assumed that the numbers are signed or unsigned. Practice exercise 1.14. Using 2's complements, find the following sums: a plus 4c plus 4 plus 11 to 11b, 4d, for plus 11 to 11 answer, plus 4000000 100 plus 4000000 100, a plus 110000 1011, c, 1111110101, plus 150000 1111 to 71111 1000, and 1 to 41111 1100 to 41111 1100, b, plus 11000 1011 d, 111110 1 plus 70000 111, 151111 1.
1.7 Binary codes. Digital systems use
signals that have two distinct values and circuit elements that have two stable states. There is a direct analogy among binary signals, binary circuit elements, and binary digits. A binary number of n digits, for example, may be represented by n binary circuit elements, each having an output signal equivalent to 0 or 1. Digital systems represent and manipulate not only binary numbers, but also many other discrete elements of information. Any discrete element of information that is distinct among a group of quantities can be represented with a binary code, i.e., a pattern of zeros and ones. The codes must be in binary because, in today's technology and in the foreseeable future, only circuits that represent and manipulate patterns of zeros and ones can be manufactured economically for use in computers. However, it must be realized that binary codes merely change the symbols, not the meaning of the elements of information that they represent. If we inspect the bits of a computer at random, we will find that most of the time they represent some type of coded information rather than binary numbers. An n-bit binary code is a group of n bits that assumes up to two n distinct combinations of ones and zeros, with each combination representing one element of the set that is being coded. A set of 4 elements can be coded with 2 bits, with each element assigned one of the following bit combinations: 00, 01, 10, and 11. A set of 8 elements requires a 3-bit code, and a set of 16 elements requires a 4-bit code. The bit combination of an n-bit code is determined from the count in binary from 0 to 2 and 1. Each element must be assigned a unique binary bit combination, and no 2 elements can have the same value. Otherwise, the code assignment will be ambiguous. Although the minimum number of bits required to code 2 n distinct quantities is n, there is no maximum number of bits that may be used for a binary code. For example, the 10 decimal digits can be coded with 10 bits, and each decimal digit can be assigned a bit combination of 9 zeros and a 1. In this particular binary code, the digit 6 is assigned the bit combination 000, 100, 0000, binary coded decimal code. Although the binary number system is the most natural system for a computer because it is readily represented in today's electronic technology, most people are more accustomed to the decimal system. One way to resolve this difference is to convert decimal numbers to binary, perform all arithmetic calculations in binary, and then convert the binary results back to decimal. This method requires that we store decimal numbers in the computer so that they can be converted to binary. Since the computer can accept only binary values, we must represent the decimal digits by means of a code that contains ones and zeros. It is also possible to perform the arithmetic operations directly on decimal numbers when they are stored in the computer in coded form. A binary code will have some unassigned bit combinations if the number of elements in the set is not a multiple power of 2. The 10 decimal digits form such a set. A binary code that distinguishes among 10 elements must contain at least 4 bits, but 6 out of the 16 possible combinations remain unassigned. Different binary codes can be obtained by arranging 4 bits into 10 distinct combinations. The code most commonly used for the decimal digits is the straight binary assignment listed in Table 1.4. This scheme is called binary coded decimal and is commonly referred to as BCD. Other decimal codes are possible, and a few of them are presented later in this section. Table 1.4 gives the 4-bit code for each decimal digit. A number with k decimal digits will require 4k bits in BCD. Decimal 396 is represented in BCD with 12 bits as 0011101010, with each group of 4 bits representing one decimal digit. A decimal number in BCD is the same as its equivalent binary number only when the number is between 0 and 9. A BCD number greater than 10 looks different from its equivalent binary number, even though both contain ones and zeros. Moreover, the binary combinations 1010 through 1111 are not used and have no meaning in BCD. Consider decimal 185 and its corresponding value in BCD and binary. 185, 10 equals 0001 1000 equals 10111001. 2. The BCD value has 12 bits to encode the characters of the decimal value, but the equivalent binary number needs only 8 bits. It is obvious that the representation of a BCD number needs more bits than its equivalent binary value. However, there is an advantage in the use of decimal numbers, because computer input and output data are generated by people who use the decimal system. It is important to realize that BCD numbers are decimal numbers and not binary numbers, although they use bits in their representation. The only difference between a decimal number and BCD is that decimals are written with the symbols 0, 1, 2, 9, and BCD numbers use the binary code 0000, 0001, 0010, 1001. The decimal value is exactly the same. Decimal 10 is represented in BCD with 8 bits as 00010000 and decimal 15 as 00010101. The corresponding binary values are 1010 and 1111 and have only 4 bits. Table 1.4 Binary Coded Decimal, BCD. Decimal BCD symbol digit 0000001010301010701110701110701110801000. 9 1001. Practice exercise 1.15. Find the BCD representation of 8410. Answer: 8410 is equal to 100100 BCD addition. Consider the addition of 2 decimal digits in BCD, together with a possible carry from a previous less significant pair of digits. Since each digit does not exceed 9, the sum cannot be greater than 9 plus 9 plus 1 is equal to 19, with 1 being a previous carry. Suppose we add the BCD digits, as if they were binary numbers. Then the binary sum will produce a result in the range from 0 to 19. In binary, this range will be from 0000 to 10011, but in BCD, it is from 0000 to 11001, with the first, i.e. leftmost, 1 being a carry, and the next 4 bits being the BCD sum. When the binary sum is equal to or less than 1001, without a carry, the corresponding BCD digit is correct. However, when the binary sum is greater than or equal to 1010, the result is an invalid BCD digit. The addition of 6 equals 0110, 2 to the binary sum converts it to the correct digit and also produces a carry as required. This is because a carry in the most significant bit position of the binary sum and a decimal carry differ by 16 minus 10 is equal to 6. Consider the following 3 BCD additions. For 0, 140, 108, 1000 plus 5 plus 0, 101. Plus 8 plus 1000 plus 9, 1000, 19, 1000, 112, 1100, 17, 10,000, and 1 plus 0, 110 plus 0, 110, 10,000, and 10, 10, 111. In each case, the 2 BCD digits are added as if they were 2 binary numbers. If the binary sum is greater than or equal to 1010, we add 0110 to obtain the correct BCD sum and a carry. In the first example, the sum is equal to 9 and is the correct BCD sum. In the second example, the binary sum produces an invalid BCD digit, 1100. The addition of 0110 produces the correct BCD sum, 0010, i.e., the number 2, and a carry. In the third example, the binary sum, 10001, produces a carry. This condition occurs when the sum is greater than or equal to 16. Although the other 4 bits are less than 1001, the binary sum requires a correction because of a carry. Adding 0110, we obtain the required BCD sum 0111, i.e., the number 7, and a BCD carry. The addition of two n-digit and signed BCD numbers follows the same procedure. Consider the addition of 184 plus 576 is equal to 760 in BCD. BCD binary sum add 6 BCD sum 10001 plus 0101, 0111, 011111 1000 0111, 10000, 01100110, 0100, 0110, 101000110000 184 plus 570, 760. The first, least significant pair of BCD digits produces a BCD digit sum of 0000 and a carry for the next pair of digits. The second pair of BCD digits plus a previous carry produces a digit sum of 0110 and a carry for the next pair of digits. The third pair of digits plus a carry produces a binary sum of 0111 and does not require correction. Practice exercise 1.16. Find the BCD sum of 4 plus 6. Answer: 10,000. Decimal arithmetic. The representation of signed decimal numbers in BCD is similar to the representation of signed numbers in binary. We can use either the familiar sign magnitude system or the sign complement system. The sign of a decimal number is usually represented with 4 bits to conform to the 4-bit code of the decimal digits. It is customary to designate a plus with 4 zeros and a minus with the BCD equivalent of 9, which is 1001. The sign magnitude system is seldom used in computers. The sign complement system can be either the 9s or the 10s complement, but the 10s complement is the one most often used. To obtain the 10s complement of a BCD number, we first take the 9s complement and then add 1 to the least significant digit. The 9s complement is calculated from the subtraction of each digit from 9. The procedures developed for the sign 2's complement system in the previous section also apply to the sign 10's complement system for decimal numbers. Addition is done by summing all digits, including the sign digit, and discarding the end carry. This operation assumes that all negative numbers are in 10's complement form. Consider the addition: plus 375 plus 240 equals plus 135, done in the sign complement system. 375 plus 9 760 135. The 9 in the leftmost position of the second number represents a minus, and 9760 is the 10's complement of 0240. The two numbers are added, and the end carry is discarded to obtain plus 135. Of course, the decimal numbers inside the computer, including the sign digits, must be in BCD. The addition is done with BCD digits as described previously. Practice exercise 1.17. Find the BCD sum. A. 370 plus 250. Answer: 0120. B. 250 plus 370. Answer: 9880. 120. The subtraction of decimal numbers, either in signed or in the sign 10's complement system, is the same as in the binary case. Take the 10's complement of the subtrahend and add it to the minuend. Many computers have special hardware to perform arithmetic calculations directly with decimal numbers in BCD. The user of the computer can specify programmed instructions to perform the arithmetic operation with decimal numbers directly, without having to convert them to binary. Other decimal codes. Binary codes for decimal digits require a minimum of 4 bits per digit. Many different codes can be formulated by arranging 4 bits into 10 distinct combinations. BCD and 3 other representative codes are shown in Table 1.5. Each code uses only 10 out of a possible 16-bit combinations that can be arranged with 4 bits. The other 6 unused combinations have no meaning and should be avoided. BCD and the 2421 code are examples of weighted codes. In a weighted code, each bit position is assigned a weighting factor in such a way that each digit can be evaluated by adding the weights of all the ones in the coded combination. The BCD code has weights of 8, 4, 2, and 1, which correspond to the power of 2 values of each bit. The bit assignment 0110, for example, is interpreted by the weights to represent decimal 6 because 8 times 0 plus 4 times 1 plus 2 times 1 plus 1 times 0 is equal to 6. The bit combination 1101, when weighted by the respective digits 2421, gives the decimal equivalent of table 1.54 different binary codes for the decimal digits. Decimal BCD digit 84212421 XS 3842 100000 0000 0011 0000100001 0001 0100 0111200010 0010 0101 0110300011 0011 0110 0101401000 0100 0111 0100501001 1011 1000 1011601110 1001 101070 111 1101 1010 1001 8100 1110 1011 100091001 1111 1100 11111010 0101 0000 00011011 0110 0001 0010 and used 1100 0111 0010 0011 bit combinations 1101 1110 1000 100 1101 1110 1100 1101 1111 1010 1111 1110 2 times 1 plus 4 times 1 plus 2 times 0 plus 1 times 1 is equal to 7. Note that some digits can be coded in two possible ways in the 2421 code. For instance, decimal 4 can be assigned to bit combination 0, 100, or 1010, since both combinations add up to a total weight of 4. BCD adders add BCD values directly, digit by digit, without converting the numbers to binary. However, it is necessary to add 6 to the result if it is greater than 9. BCD adders require significantly more hardware and no longer have a speed advantage of conventional binary adders. 5. The 2421 and the XS3 codes are examples of self-complementing codes. Such codes have the property that the nines complement of a decimal number is obtained directly by changing ones to zeros and zeros to ones, i.e., by complementing each bit in the pattern. For example, the codes in Table 1.5 indicate that decimal 395 is represented in the XS3 code as 0110, 1100, 1000. Its nines complement, 604, is represented as 1001, 0011, 0111, which is obtained simply by complementing each bit of the code for 395, as with the ones complement of binary numbers. The XS3 code has been used in some older computers because of its self-complementing property. XS3 is an unweighted code in which each coded combination is obtained from the corresponding binary value plus 3. Note that the BCD code is not self-complementing. The 8421 code is an example of assigning both positive and negative weights to a decimal code. In this case, the bit combination 0110 is interpreted as decimal 2 and is calculated from 8*0 plus 4 by 1 plus 2 *1 plus 1 *0 is equal to 2. Gray code. The output data of many physical systems are quantities that are continuous. These data must be converted into digital form before they are applied to a digital system. Continuous or analog information is converted into digital form by means of an analog-to-digital converter. It is sometimes convenient to use the gray code shown in Table 1.6 to represent digital data that have been converted from analog data. The advantage of the gray code over the straight binary number sequence is that only one bit in the code group changes in going from one number to the next. For example, in going from 7 to 8, the gray code changes from 100 to 1100. Only the first bit changes, from 0 to 1. The other 3 bits remain the same. By contrast, with binary numbers, the change from 7 to 8 will be from 0111 to 1000, which causes all 4 bits to change values. The gray code is used in applications in which the normal sequence of binary numbers generated by the hardware may produce an error or ambiguity during the transition from one number to the next. If binary numbers are used, a change, for example, from 0111 to 1000 may produce an intermediate erroneous number 1001 if the value of the rightmost bit takes longer to change than do the values of the other 3 bits. This could have serious consequences for the machine using the information. The gray code eliminates this problem, since only one bit changes its value during any transition between two numbers. A typical application of the gray code is the representation of analog data by a continuous change in the angular position of a shaft. The shaft is partitioned into segments. Table 1.6 Gray code Gray decimal code equivalent 00000000110011030110501071108110191111110. 1110 1000 10 12 1000 11 13 1001 14 1015. And each segment is assigned a number. If adjacent segments are made to correspond with the gray code sequence, ambiguity is eliminated between the angle of the shaft and the value encoded by the sensor. ASCII character code. Many applications of digital computers require the handling not only of numbers, but also of other characters or symbols, such as the letters of the alphabet. For instance, consider a high-tech company with thousands of employees. To represent the names and other pertinent information, it is necessary to formulate a binary code for the letters of the alphabet. In addition, the same binary code must represent numerals and special characters, such as $. An alphanumeric character set is a set of elements that includes the 10 decimal digits, the 26 letters of the alphabet, and a number of special characters. Such a set contains between 36 and 64 elements if only capital letters are included.
Such a set contains between 36 and 64 elements if only capital.
Such a set contains between 36 and 64 elements if only capital letters are included, or between 64 and 128 elements if both uppercase and lowercase letters are included. In the first case, we need a binary code of 6 bits, and in the second, we need a binary code of 7 bits. The standard binary code for the alphanumeric characters is the American Standard Code for Information Interchange, ASCII, which uses 7 bits to code 128 characters, as shown in Table 1.7. The 7 bits of the code are designated by B1 through B7, with B7 being the most significant bit. The letter A, for example, is represented in ASCII as 1000001, column 100, row 0001. The YesCII code also contains 94 graphic characters that can be printed and 34 non-printing characters used for various control functions. Table 1.7 American Standard Code for Information Interchange, ASCII, B7, B6, B5, B4, B3, B2, B1, 0, 0, 0, 0, 0, 1, 0, 10, 0, 11, 100 billion, 101 million, 110,000, 111, 0, 0, 0, 0, NULDLESP0 at P, P0, 0, 0, 1, SLHDC1. 1AQAQ0010 SDXDC2, 2B RB R0011. ETX DC3 number 3CSCS 0100 YOT DC4 $4 DTDT 0101 YNQ NAK %5 EU EU 0110 ACK SYN and 6F VF V0111 Bell EAT B 7 GW 1000 BS CAN 8HX HX 1001 HTM 9 IY 1010 LF sub asterisk JZJ Z1011 VT ESC plus KK 1100 FFFS 6L L1101 CRGS equals M 1110 SORS 7N and 1111 SIUS / ODEL control characters NUL null DLE data link escape SWH start of heading DC1 device control 1 SDX start of text DC2 device control 2 ETX end of text DC3 device control 3 YOT end of transmission DC4 device control 4 YNQ inquiry NAK negative acknowledge ACK acknowledge SYN synchronous idle BL Bell EAT B end of transmission block BS backspace can cancel HT horizontal tab EM end of medium LF line feed SUB substitute VT vertical tab ESC escape FF form feed FS file separator CR carriage return GS group separator SO shift out RS record separator SI shift in US unit separator SP space del delete. Graphic characters consist of the 26 uppercase letters A through Z, the 26 lowercase letters A through Z, the 10 numerals 0 through 9, and 32 special printable characters such as %, asterisk, and $. The 34 control characters are designated in the ASCII table with abbreviated names. They are listed again below the table with their functional names. The control characters are used for routing data and arranging the printed text into a prescribed format. There are 3 types of control characters: format effectors, information separators, and communication control characters. Format effectors are characters that control the layout of printing. They include the familiar word processor and typewriter controls such as backspace, BS, horizontal tabulation, HT, and carriage return, CR. Information separators are used to separate the data into divisions such as paragraphs and pages. They include characters such as record separator, RS, and file separator, FS. The communication control characters are useful during the transmission of text between remote devices so that it can be distinguished from other messages using the same communication channel before it and after it. Examples of communication control characters are STX, start of text, and ETX, end of text, which are used to frame a text message transmitted through a communication channel. ASCII is a 7-bit code, but most computers manipulate an 8-bit quantity as a single unit called a byte. Therefore, ASCII characters most often are stored 1 per byte. The extra bit is sometimes used for other purposes, depending on the application. For example, some printers recognize 8-bit ASCII characters with the most significant bit set to 0. An additional 128 8-bit characters with the most significant bit set to 1 are used for other symbols, such as the Greek alphabet or italic type font. Error detecting code. To detect errors in data communication and processing, an 8th bit is sometimes added to the ASCII character to indicate its parity. A parity bit is an extra bit included with a message to make the total number of ones either even or odd. Consider the following 2 characters and their even and odd parity. With even parity. With odd parity, ASCII equals 100 000 101000 11100001. ASCII T equals 101 0100 1101000 In each case, we insert an extra bit in the leftmost position of the code to produce an even number of ones in the character for even parity or an odd number of ones in the character for odd parity. In general, one or the other parity is adopted, with even parity being more common. The parity bit is helpful in detecting errors during the transmission of information from one location to another. This function is handled by generating an even parity bit at the sending end for each character. The 8-bit characters that include parity bits are transmitted to their destination. The parity of each character is then checked at the receiving end. If the parity of the received character is not even, then at least one bit has changed value during the transmission. This method detects 1, 3, or any odd combination of errors in each character that is transmitted. An even combination of errors, however, goes undetected, and additional error detection codes may be needed to take care of that possibility. What is done after an error is detected depends on the particular application. One possibility is to request retransmission of the message on the assumption that the error was random and will not occur again. Thus, if the receiver detects a parity error, it sends back the ASCII NAK, negative acknowledge, control character consisting of an even parity 8 bits 100100101. If no error is detected, the receiver sends back an ACK, acknowledge, control character, namely 00000110. The sending end will respond to an NAK by transmitting the message again until the correct parity is received. If, after a number of attempts, the transmission is still in error, a message can be sent to the operator to check for malfunctions in the transmission path. Practice exercise 1.18. What is the even parity bit of A equals 0101100? Answer: 11.8 binary storage and registers. The binary information in a digital computer must have a physical existence in some medium for storing individual bits. A binary cell is a device that possesses two stable states and is capable of storing one bit, 0 or 1, of information. The input to the cell receives excitation signals that set it to one of the two states. The output of the cell is a physical quantity that distinguishes between the two states. The information stored in a cell is 1 when the cell is in one stable state and 0 when the cell is in the other stable state. Registers. A register is a contiguous group of binary cells. A register with n cells can store a discrete quantity of information that contains n bits. The state of a register is an n-tuple of ones and zeros, with each bit designating the state of one cell in the register. The content of a register is a function of the interpretation given to the information stored in it. Consider, for example, a 16-bit register with the following binary content: 1100001111001001. A register with 16 cells can be in one of 216 possible states. If one assumes that the content of the register represents a binary integer, then the register can store any binary number from 0 to 216 to 1. For the particular example shown, the content of the register is the binary equivalent of the decimal number.
For the particular example shown, the content of the register is the binary.
For the particular example shown, the content of the register is the binary equivalent of the decimal number 50,121. If one assumes instead that the register stores alphanumeric characters of an 8-bit code, then the content of the register is any two meaningful characters. For the ASCII code with an even parity placed in the 8th most significant bit position, the register contains the two characters C, the leftmost 8 bits, and I, the rightmost 8 bits. If, however, one interprets the content of the register to be 4 decimal digits represented by a 4-bit code, then the content of the register is a 4-digit decimal number. In the XS3 code, the register holds the decimal number 9096. The content of the register is meaningless in BCD because the bit combination 1100 is not assigned to any decimal digit. From this example, it is clear that a register can store discrete elements of information and that the same bit configuration may be interpreted differently for different types of data depending on the application. Register transfer. A digital system is characterized by its registers and the components that perform data processing. In digital systems, a register transfer operation is a basic operation that consists of a transfer of binary information from one set of registers into another set of registers. The transfer may be direct, from one register to another, or may pass through data processing circuits to perform an operation. Figure 1.1 illustrates the transfer of information among registers and demonstrates pictorially the transfer of binary information from a keyboard into a register in the memory unit. The input unit is assumed to have a keyboard, a control circuit, and an input register. Each time a key is struck, the memory unit, processor unit, input unit, JOHN, memory register, 8 cells, 8 cells, 8 cells, 8 cells, 8 cells, keyboard, control 0, 1 0 0 1 0 1 0 0 1 0 0 1 1 1 1 1 1 0 0 1 0 0 0 1 1 0 0 1 1 1 0 processor register, input register, John. Figure 1.1. Transfer of information among registers. Control circuit enters an equivalent 8-bit alphanumeric character code into the input register. We shall assume that the code used is the ASCII code with an odd parity bit. The information from the input register is transferred into the 8 least significant cells of a processor register. After every transfer, the input register is cleared to enable the control to insert a new 8-bit code when the keyboard is struck again. Each 8-bit character transferred to the processor register is preceded by a shift of the previous character to the next 8 cells on its left. When a transfer of 4 characters is completed, the processor register is full, and its contents are transferred into a memory register. The contents stored in the memory register shown in Fig. 1.1 came from the transfer of the characters J, O, H, and N after the 4 appropriate keys were struck. To process discrete quantities of information in binary form, a computer must be provided with devices that hold the data to be processed and with circuit elements that manipulate individual bits of information. The device most commonly used for holding data is a register. Binary variables are manipulated by means of digital logic circuits. Figure 1.2 illustrates the process of adding two 10-bit binary numbers. The memory unit. Memory unit, processor unit, operand 1, operand 2, sum R1, R2, R3, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1. 00011 digital logic circuits for binary addition. Figure 1.2. Example of registers in binary information processing, which normally consists of millions of registers, is shown with only 3 of its registers. The part of the processor unit shown consists of 3 registers, R1, R2, and R3, together with digital logic circuits that manipulate the bits of R1 and R2 and transfer into R3 a binary number equal to their arithmetic sum. Memory registers store information and are incapable of processing the 2 operands. However, the information stored in memory can be transferred to processor registers, and the results obtained in processor registers can be transferred back into a memory register for storage until needed again. The diagram shows the contents of 2 operands transferred from 2 memory registers into R1 and R2. The digital logic circuits produce the sum, which is transferred to register R3. The contents of R3 can now be transferred back to one of the memory registers. The last 2 examples demonstrated the information flow capabilities of a digital system in a simple manner. The registers of the system are the basic elements for storing and holding the binary information. Digital logic circuits process the binary information stored in the registers. Digital logic circuits and registers are covered in chapters 2 through 6. The memory unit is explained in Chapter 7. The description of register operations at the register transfer level and the design of digital systems are covered in Chapter 8. 1.9. Binary logic. Binary logic deals with variables that take on 2 discrete values and with operations that assume logical meaning. The 2 values the variables assume may be called by different names: true and false, yes and no, etc. but for our purpose, it is convenient to think in terms of bits and assign the values 1 and 0. The binary logic introduced in this section is equivalent to an algebra called Boolean algebra. The formal presentation of Boolean algebra is covered in more detail in Chapter 2. The purpose of this section is to introduce Boolean algebra in a heuristic manner and relate it to digital logic circuits and binary signals. Definition of binary logic. Binary logic consists of binary variables and a set of logical operations. The variables are designated by letters of the alphabet, such as A, B, C, X, Y, Z, etc., with each variable having two and only two distinct possible values, 1 and 0. There are three basic logical operations, and, or, and not. Each operation produces a binary result, denoted by Z. 1. And this operation is represented by a dot or by the absence of an operator. For example, X hashtag Y equals Z or XY equals Z is read, X and Y is equal to Z. The logical operation and is interpreted to mean that Z equals 1 if and only if X equals 1 and Y equals 1. Otherwise, Z equals 0. Remember that X, Y, and Z are binary variables and can be equal either to 1 or 0 and nothing else. The result of the operation X hashtag Y is Z. 2. Or, this operation is represented by a plus sign. For example, X plus Y equals Z is read X or Y is equal to Z, meaning that Z equals 1 if X equals 1 or if Y equals 1 or if both X equals 1 and Y equals 1. If both X equals 0 and Y equals 0, then Z equals 0. Table 1.8 Truth tables of logical operations and or not X Y X hashtag YX YX plus YXX 0 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 1 0 0 1 0 1 1 1 1 1 1 1. 3. Not. This operation is represented by a prime, sometimes by an overbar. For example, X equals Z or X equals Z is read not X is equal to Z, meaning that Z is what X is not. In other words, if X equals 1, then Z equals 0, but if X equals 0, then Z equals 1. The not operation is also referred to as the complement operation, since it changes a 1 to 0 and a 0 to 1, that is, the result of complementing 1 is 0, and vice versa. Binary logic resembles binary arithmetic, and the operations and or have similarities to multiplication and addition, respectively. In fact, the symbols used for and or are the same as those used for multiplication and addition. However, binary logic should not be confused with binary arithmetic. One should realize that an arithmetic variable designates a number that may consist of many digits. A logic variable is always either 1 or 0. For example, in binary arithmetic, we have 1 plus 1 is equal to 10, read 1 plus 1 is equal to 2, whereas in binary logic, we have 1 plus 1 is equal to 1, read 1 or 1 is equal to 1. For each combination of the values of X and Y, there is a value of Z specified by the definition of the logical operation. Definitions of logical operations may be listed in a compact form called truth tables. A truth table is a table of all possible combinations of the variables, showing the relation between the values that the variables may take and the result of the operation. The truth tables for the operations and or with variables X and Y are obtained by listing all possible values that the variables may have when combined in pairs. For each combination, the result of the operation is then listed in a separate row. The truth tables for and, or, and not are given in Table 1.8. These tables clearly demonstrate the definition of the operations. Logic gates. Logic gates are electronic circuits that operate on one or more physical input signals to produce an output signal. Electrical signals such as voltages or currents exist as analog signals having values over a given continuous range, say 0 to 3V. But in a digital system, these voltages are interpreted to be either of two recognizable values, 0 or 1. Voltage-operated logic circuits respond to two separate voltage levels that represent a binary variable equal to logic 1 or logic 0. For example, a particular digital system may define logic 0 as a signal equal to 0V and logic 1 as a signal equal to 3V. In practice, each voltage level has an acceptable range, as shown in Fig. 1.3, the input terminals. Volts 3 to 1 transition occurs between these limits. 0 Figure 1.3 signal levels for binary logic values. Signal range for logic 1. Signal range for logic 0. Z, X, Z5X.
Y5X1 YXX9Y.
A. 2 input and gate. B. 2 input or gate. C. Not gate or inverter. Figure 1.4 symbols for digital logic circuits. Of digital circuits, accept binary signals within the allowable range and respond at the output terminals with binary signals that fall within the specified range. The intermediate region between the allowed regions is crossed only during a state transition. Any desired information for computing or control can be operated on by passing binary signals through various combinations of logic gates, with each signal representing a particular binary variable. When the physical signal is in a particular range, it is interpreted to be either a 0 or a 1. The graphic symbols used to designate the three types of gates are shown in Figure 1.4. The gates are blocks of hardware that produce the equivalent of logic 1 or logic 0 output signals if input logic requirements are satisfied. The input signals X and Y in the and or gates may exist in one of four possible states: 0, 0, 10, 11, or 0, 1. These input signals are shown in Fig. 1.5 together with the corresponding output signal for each gate. The timing diagrams illustrate the idealized response of each gate to the four input signal combinations. The horizontal axis of the timing diagram represents the time, and the vertical axis shows the signal as it changes between the two possible voltage levels. In reality, the transitions between logic values occur quickly but not. Problems 53x 0, 1, 1, 0, 0, y 0, 0, 1, 1, 0, and x y 0, 0, 1, 0, 0, or x 1, y 0, 1, 1, 1, 0 not. X 9, 1, 0, 0, 1, 1. Figure 1.5 input-output signals for gates A, B, C, D, F, 5, A, B, C, G, 5, A, 1, B, 1, C, 1, D, A, B, C. A, 3 input and gate, B, 4 input or gate. Figure 1.6 gates with multiple inputs. Instantaneously, the low level represents logic 0 and the high level logic 1. The AND gate responds with a logic 1 output signal when both input signals are logic 1. The OR gate responds with a logic 1 output signal if any input signal is logic 1. The NOT gate is commonly referred to as an inverter. The reason for this name is apparent from the signal response in the timing diagram, which shows that the output signal inverts the logic sense of the input signal. And OR gates may have more than two inputs. An AND gate with 3 inputs and an OR gate with 4 inputs are shown in Figure 1.6. The 3-input AND gate responds with logic 1 output if all 3 inputs are logic 1. The output produces logic 0 if any input is logic 0. The 4-input OR gate responds with logic 1 if any input is logic 1. Its output becomes logic 0 only when all inputs are logic 0. Problems. Answers to problems marked with asterisk appear at the end of the text. 1.1 List the octal and hexadecimal numbers from 5010 to 6410. Using A, B, C, and D for the last 4 digits, list the numbers from 1110 to 3010 in base 14. 1.2 asterisk What is the exact number of bytes in a system that contains A, 16K bytes, B, 32M bytes, and C, 2G bytes? 1.3 Convert the following numbers with the indicated bases to decimal. A, asterisk 1203, 4, B, asterisk 5243, 6, C, 9922, 14, D, 248, 9. 1.4 What is the largest binary number that can be expressed with 12 bits? What are the equivalent decimal, octal, and hexadecimal numbers? 1.5 asterisk determine the base of the numbers in each case for the following operations to be correct. A. 67 divided by 5 is equal to 11. B. 15 times 3 is equal to 51. C. 123 plus 120 is equal to 303. X2. 1.6 asterisk the solutions to the quadratic equation 13x plus 22 is equal to 0 are x equals 7 and x equals 2. What is the base of the numbers? 1.7 asterisk convert the hexadecimal number CA5E to binary and then convert it from binary to octal. 1.8 convert the decimal number 253 to binary in two ways. A. Convert directly to binary. B. Convert first to hexadecimal and then from hexadecimal to binary. Which method is faster? 1.9 express the following numbers in decimal. A. Asterisk 10,101.101. 2. B. Asterisk 64.8. 16. C. Asterisk 261.44. 8. D. 51. D. C. 16. E. 110,011.001. 2. 1.10 convert the following binary numbers to hexadecimal and to decimal. A. 1.00011. B. 1000.11. Explain why the decimal answer in B is 8 times that in A. 1.11 perform the following division in binary. 101010 100. 1.12 asterisk add and multiply the following numbers without converting them to decimal. A. Binary numbers 1101 and 110. B. Hexadecimal numbers D0 and 1F. 1.13 perform the following conversion problems. A. Convert decimal 45.125 to binary. B. Calculate the binary equivalent of 3.33 out to 4 places. Then convert from binary to decimal. Find the error percentage. C. Convert the binary result in B into hexadecimal. Then convert the result to decimal. Is the answer the same? 1.14 obtain the ones and twos complements of the following binary numbers. A. 1110010. B. 0001100. C. 10111101. D. 10100101. E. 11000011. F. 0101100. 1.15 find the nines and the tens complement of the following decimal numbers. A. 65,234,035. B. 56,783,223. C. 87,367. D. 99,999,001.16. A. Find the eights complement of 2360. 8. B. Convert 2360, 8 to binary. C. Find the twos complement of the result in B. D. Convert the answer in C to octal and compare with the answer in A. 1.17 perform subtraction on the given and sign numbers using the tens complement of the subtrahend. Where the result should be negative, find its tens complement and affix a minus sign. Verify your answers. A. 7,523 to 4.567. B. 230 to 1,204. C. 224 to 712. D. 2,390 to 945. Problems 55. 1.18 perform subtraction on the given and signed binary numbers using the twos complement of the subtrahend. Where the result should be negative, find its twos complement and affix a minus sign. A. 11,001 to 10,010. B. 1,100 to 111,100. C. 10,101 to 11,011. D. 110. 0011. 10001. 1.19 asterisk the following decimal numbers are shown in sign magnitude form, plus 9,286 and plus 801. Convert them to sine tens complement form and perform the following operations. Note that the sum is plus 10,627 and requires 5 digits and a sign. A. Plus 9,286 plus 801. B. Plus 9,286 plus 801. C. 9,286 plus 801. D. 9,286 plus 801. 1.20 Convert decimal plus 49 and plus 29 to binary, using the sine 2's complement representation and enough digits to accommodate the numbers. Then perform the binary equivalent of plus 29 plus 49, 29 plus 49, and 29 plus 49. Convert the answers back to decimal and verify that they are correct. 1.21 If the numbers plus 9,742, 10 and plus 641, 10 are in sign magnitude format, their sum is plus 10,383, 10, and requires 5 digits and a sign. Convert the numbers to sine tens complement form and find the following sums. A. Plus 9,742 plus 641. B. Plus 9,742 plus 641. C. 9,742 plus 641. D. 9,742 plus 641. 1.22 Convert decimal 9,045 and 337 to both BCD and ASCII codes. For ASCII, an even parity bit is to be appended at the left. 1.23 Represent the unsigned decimal numbers 609 and 516 in BCD, and then show the steps necessary to form their sum. 1.24 Formulate a weighted binary code for the decimal digits, using the following weights. A. Asterisk 5, 2, 1, 1b, 6, 3, 2, 1. 1.25 Represent the decimal number 6,428 in A. BCD, B. XS 3 code, C. 2421 code, and D. 6,311 code. 1.26 Find the nines complement of the decimal number 6,248 and express it in 2421 code. Show that the result is the ones complement of the answer to C in problem 1.25. This demonstrates that the 2421 code is self-complementing. 1.27 Assign a binary code in some orderly manner to the 52 playing cards. Use the minimum number of bits. 1.28 The message pass 0.12 is to be sent via communication line. For this, each character of the message should be encoded into a 7-bit ASCII code, including the period and the space. Each SCII encoded character should be then encrypted by adding binary 101 to it. Write the expression for the message sent. 1.29 asterisk decode the following ASCII code. 100 00110110 1110100 001010 00011000 001010 001010 001010 011100 0101. 1.30 The following is a string of ASCII characters whose bit patterns have been converted into hexadecimal for compactness. 47-2E5C42CF Of the 8 bits in each pair of digits, the leftmost is a parity bit. The remaining bits are the ASCII code. A. Convert the string to bit form and decode the SCI. B. Determine the parity used, odd or even. 1.30 asterisk How many printing characters are there in ESCI? How many of them are special characters, not letters or numerals? 1.32 asterisk What bit must be complemented to change an ASCII letter from capital to lowercase and vice versa? 1.33 asterisk The state of a 16-bit register is 10001110101101. What is its content if it represents A. 4 decimal digits in BCD. B. 4 decimal digits in the XS3 code. C. 4 hexadecimal digits in the gray code. D. 2 ESCI characters with even parity bit as the leftmost bit in each byte. 1.34. A. List the ASCII code for the 10 decimal digits with an even parity bit in the leftmost position. B. Repeat. A. With odd parity. References 1. Kavanaugh, J. 1984. Digital Computer Arithmetic. New York, McGraw-Hill. 2. Mano, M. 1988. Computer Engineering. Hardware Design. Englewood Cliffs, N.J. Prentice Hall. 3. Nelson v. P. H. T. Nagel, J.D. Irwin, and V.D. Carroll. 1997. Digital Logic Circuit Analysis and Design. Upper Saddle River, New Jersey. Prentice Hall.
4. Schmidt, H. 1974.
Decimal Computation. New York, John Wiley. 5. Katz, R. H. and Borriello, G. 2004. Contemporary Logic Design, 2nd edition, Upper Saddle River, New Jersey. Prentice Hall. Web Search Topics. 2's Complement ASCII BCD Edition BCD Code Binary Edition Binary Codes Binary Logic Binary Numbers Computer Arithmetic Error Correction XS 3 Code Gray Code Logic Gate Parity Bit Radix Complement. Shaft Encoder Storage Register. Chapter 2 Boolean Algebra and Logic Gates. Chapter Objectives 1. Gain a basic understanding of postulates used to form algebraic structures. 2. Understand the Huntington postulates. 3. Understand the basic theorems and postulates of Boolean algebra. 4. Know how to develop a logic diagram from a Boolean function. Know how to derive a Boolean function from a logic diagram. 5. Know how to apply De Morgan's theorems. 6. Know how to express a Boolean function as a truth table. Know how to derive a Boolean function from a truth table. 7. Know how to express a Boolean function as a sum of minterms and as a product of max terms. 8. Be able to convert from a sum of minterms to a product of max terms and vice versa. 9. Be able to form a two-level gate structure from a Boolean function in sum of products form. Know how to form a two-level gate structure from a Boolean function in product of sums form. 10. Be able to implement a Boolean function with NAND and inverter gates. Know how to implement a Boolean function with NOR and inverter gates. 2.1 Introduction. The cost of circuits that implement binary logic in all of today's digital devices and computers is an important factor addressed by designers, be they computer engineers, electrical engineers, or computer scientists. Finding simpler and cheaper, but equivalent, realizations of a circuit can reap huge payoffs in reducing the overall cost of the design. Mathematical methods that simplify circuits rely primarily on Boolean algebra. Therefore, this chapter provides a basic vocabulary and a brief foundation in Boolean algebra that will enable you to optimize simple circuits and to understand the purpose of algorithms used by software tools to optimize complex circuits involving millions of logic gates. 2.2 Basic definitions. Boolean algebra, like any other deductive mathematical system, may be defined with a set of elements, a set of operators, and a number of unproved axioms or postulates. A set of elements is any collection of objects, usually having a common property. If S is a set and X and Y are certain objects, then the notation XS means that X is a member of the set S, and YS means that Y is not an element of S. A set with a denumerable number of elements is specified by braces. Equals 1, 2, 3, 4 indicates that the elements of set A are the numbers 1, 2, 3, and 4. A binary operator defined on a set S of elements is a rule that assigns, to each pair of elements from S, a unique element from S. As an example, consider the relation A** B equals C. We say that asterisk is a binary operator if it specifies a rule for finding C from the pair A, B, and also if A, B, CS. However, Asterisk is not a binary operator if A, B, S, and if C, S. The postulates of a mathematical system form the basic assumptions from which it is possible to deduce the rules, theorems, and properties of the system. The most common postulates used to formulate various algebraic structures are as follows. Closure. A set S is closed with respect to a binary operator if, for every pair of elements of S, the binary operator specifies a rule for obtaining a unique element of S. For example, the set of natural numbers n equals 1, 2, 3, 4, C is closed with respect to the binary operator plus by the rules of arithmetic addition, since for any A, B there is a unique Cn such that A plus B equals C. The set of natural numbers is not closed with respect to the binary operator by the rules of arithmetic subtraction because 2 to 3 equals 1 and 2, 3n, but 1n. 2. Associative law. A binary operator asterisk on a set S is said to be associative whenever x asterisk y asterisk z equals x asterisk y asterisk z for all x, y, zs. 3. Commutative law. A binary operator asterisk on a set S is said to be commutative whenever x asterisk y equals y asterisk x for all x, ys. 4. Identity element. A set S is said to have an identity element with respect to a binary operation asterisk on S if there exists an element ES with the property that E asterisk x equals x asterisk E equals x for every XS example. The element 0 is an identity element with respect to the binary operator plus on the set of integers I equals C, 3, 2, 1, 0, 1, 2, 3, C, since x plus 0 is equal to 0 plus x equals x for any xi. The set of natural numbers, n, has no identity element, since 0 is excluded from the set. 5. Inverse. A set S having the identity element E with respect to a binary operator asterisk is said to have an inverse whenever, for every xs, there exists an element ys such that x asterisk y equals E. Example. In the set of integers I and the operator plus with E equals 0, the inverse of an element A is A, since A plus A equals 0. 6. Distributive law. If asterisk and hashtag are two binary operators on a set S, asterisk is said to be distributive over hashtag whenever 0, hashtag Z, hashtag X asterisk, Y equals X asterisk Y, X asterisk Z. A field is an example of an algebraic structure. A field is a set of elements, together with two binary operators, each having properties 1 through 5 and both operators combining to give property 6. The set of real numbers, together with the binary operators plus and hashtag, forms the field of real numbers. The field of real numbers is the basis for arithmetic and ordinary algebra. The operators and postulates have the following meanings. The binary operator plus defines addition. The additive identity is 0. The additive inverse defines subtraction. The binary operator hashtag defines multiplication. The multiplicative identity is 1. For the multiplicative inverse of A equals 1 slash A defines division, i.e., A hashtag 1 slash A equals 1. The only distributive law applicable is that of hashtag over plus. A hashtag B hashtag C plus C equals A plus, a 2.3 A Ziomat IC definition of Boolean algebra. In 1854, George Boole developed an algebraic system now called Boolean algebra. In 1938, Claude E. Shannon introduced a two-valued Boolean algebra called switching algebra that represented the properties of bistable electrical switching circuits. For the formal definition of Boolean algebra, we shall employ the postulates formulated by E.V. Huntington in 1904. Boolean algebra is an algebraic structure defined by a set of elements, B, together with two binary operators, plus and hashtag, provided that the following Huntington postulates are satisfied. 1. A. The structure is closed with respect to the operator plus. B. The structure is closed with respect to the operator hashtag. 2. A. The element 0 is an identity element with respect to plus. that is, x plus 0 is equal to 0 plus x equals x. Hashtag x number 1 1 hashtag x. B, the element 1 is an identity element with respect to that is equals x. 3. A, the structure is commutative with respect to plus, that is x plus y equals y plus x. Hashtag x hashtag y hashtag x. B, the structure is commutative with respect to that is equals. 4. A, hashtag x hashtag y hashtag y, hashtag the operator is distributive over plus, that is plus x, xc equals plus c. Hashtag z, hashtag x. B, the operator plus is distributive over that is x plus y equals x plus y plus c. 5. For every element xb, there exists an element xb called the complement of x such that a, x plus x equals 1 and b, x hashtag x equals 0. 6. There exist at least two elements x, y, b such that xy. Comparing Boolean algebra with arithmetic and ordinary algebra, the field of real numbers, we note the following differences. 1. Huntington postulates do not include the associative law. However, this law holds for Boolean algebra and can be derived, for both operators, from the other postulates. 2. Hashtag z, hashtag x. The distributive law of plus over, i.e., x plus y equals x plus y plus c, is valid for Boolean algebra but not for ordinary algebra. 3. Boolean algebra does not have additive or multiplicative inverses. Therefore, there are no subtraction or division operations. 4. Postulate 5 defines an operator called the complement that is not available in ordinary algebra. 5. Ordinary algebra deals with the real numbers, which constitute an infinite set of elements. Boolean algebra deals with the as-yet undefined set of elements, b, but in the two-valued Boolean algebra defined next, and of interest in our subsequent use of that algebra. B is defined as a set with only two elements, 0 and 1. Boolean algebra resembles ordinary algebra in some respects. The choice of the symbols plus and hashtag is intentional to facilitate Boolean algebraic manipulations by persons already familiar with ordinary algebra. Although one can use some knowledge from ordinary algebra to deal with Boolean algebra, the beginner must be careful not to substitute the rules of ordinary algebra where they are not applicable. It is important to distinguish between the elements of the set of an algebraic structure and the variables of an algebraic system. For example, the elements of the field of real numbers are numbers, whereas variables such as a, b, c, etc., used in ordinary algebra, are symbols that stand for real numbers. Similarly, in Boolean algebra, one defines the elements of the set B, and variables such as x, y, and z are merely symbols that represent the elements. At this point, it is important to realize that, in order to have a Boolean algebra, one must show that 1. The elements of the set B, 2. The rules of operation for the two binary operators, and 3. The set of elements, B, together with the two operators, satisfy the 6 Huntington postulates. One can formulate many Boolean algebras, depending on the choice of elements of B and the rules of operation. In our subsequent work, we deal only with a two-valued Boolean algebra, i.e., a Boolean algebra with only two elements. Two-valued Boolean algebra has applications in set theory, the algebra of classes, and in propositional logic. Our interest here is in the application of Boolean algebra to gate-type circuits commonly used in digital devices and computers. Two-valued Boolean algebra. A two-valued Boolean algebra is defined on a set of two elements, b equals 0, 1, with rules for the two binary operators plus and hashtag as shown in the following operator tables. The rule for the complement operator is for verification of postulate 5x, y, x, y, x, y, y, x, 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 0, 0, 0, 0, 0. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1. These rules are exactly the same as the and, or, and not operations, respectively, defined in Table 1.8. We must now show that the Huntington postulates are valid for the set B equals 0, 1, and the two binary operators plus and hashtag. 1. That the structure is closed with respect to the two operators is obvious from the tables, since the result of each operation is either 1 or 0 and 1, 0 b. 2. From the tables we see that a 0 plus 0 is equal to 0, 0 plus 1 is equal to 1 plus 0 is equal to 1. 1 number 1, 1 number 0, 0 number 1, b equals 1 equals 0. Hashtag. This establishes the two identity elements, 0 for plus and 1 for as defined by postulate 2. 3. The commutative laws are obvious from the symmetry of the binary operator tables. 4. A x hashtag y hashtag y hashtag z. The distributive law plus x z equals plus can be shown to hold from the operator tables by forming a truth table of all possible values of x, y, and z. For each combination, we derive x hashtag y plus z and show that the value is the same as the value of x hashtag y plus x hashtag z x yx yz 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 yz 0 1 1 1 0 1 1 1 0 0 0 0 0 1 1 1 x y xz x xz 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 1 1 0 1 1 1 1. Hashtag b. The distributive law of plus over can be shown to hold by means of a truth table similar to the one in 4. A x hashtag y hashtag y hashtag z. The distributive law plus x z equals plus can be shown to hold from the operator tables by forming a truth table of all possible values of x, y, and z. For each combination, we derive x hashtag y plus z and show that the value is the same as the value of x hashtag y plus x hashtag zz x yx yz 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 yz 0 1 1 1 0 1 1 1 0 0 0 0 0 1 1 1 x y xz 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 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 1 1 0 1 1 1 1
0 1 1 1 0 1 1 1 0 0
0 1 1 1 0 1 1 1 0 0 0 0 0 1 1 1 x y xz xz 0
0 1 1 1 0 1 1 1 0 0 0 0 0 1 1 1 x y x z x y x z 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1 1 1 0 1 1 1 1. Hashtag b.
Hashtag b. The distributive law of plus over can be shown to hold by means of a truth table similar to the one in part A. 5. From the complement table, it is easily shown that plus 1 equals plus x equals 1, since 0 plus 0 is equal to 1, and 1 plus 1 equals a. x 0 1 plus 0 is equal to 1. X hashtag x 0 number 0 0 number 1 1 number 1 1 number 0, b equals 0, since equals 0 and equals 0. Thus, postulate 5 is verified. 6. Postulate 6 is satisfied because the two-valued Boolean algebra has two elements, 1 and 0, with 1 0. We have just established a two-valued Boolean algebra having a set of two elements, 1 and 0, two binary operators with rules equivalent to the and or operations, and a complement operator equivalent to the not operator. Thus, Boolean algebra has been defined in a formal mathematical manner and has been shown to be equivalent to the binary logic presented heuristically in section 1.9. The heuristic presentation is helpful in understanding the application of Boolean algebra to gate-type circuits. The formal presentation is necessary for developing the theorems and properties of the algebraic system. The two-valued Boolean algebra defined in this section is also called switching algebra by engineers. To emphasize the similarities between two-valued Boolean algebra and other binary systems, that algebra was called binary logic in section 1.9. From here on, we shall drop the adjective two-valued from Boolean algebra in subsequent discussions. 2.4b Basic Theorems and Properties of Boolean Algebra Duality. In Section 2.3, the Huntington postulates were listed in pairs and designated by Part A and Part B. One part may be obtained from the other if the binary operators and the identity elements are interchanged. This important property of Boolean algebra is called the duality principle and states that every algebraic expression deducible from the postulates of Boolean algebra remains valid if the operators and identity elements are interchanged. In a two-valued Boolean algebra, the identity elements and the elements of the set B are the same, 1 and 0. The duality principle has many applications. If the dual of an algebraic expression is desired, we simply interchange or and operators and replace ones by zeros and zeros by ones. Basic theorems. Table 2.1 lists 6 theorems of Boolean algebra and 4 of its postulates. The notation is simplified by omitting the binary operator whenever doing so does not lead to confusion. The theorems and postulates listed are the most basic relationships in Boolean algebra. The theorems, like the postulates, are listed in pairs. Each relation is the dual of the one paired with it. The postulates are basic axioms of the algebraic structure and need no proof. The theorems must be proven from the postulates. Proofs of the theorems with one variable are presented next. At the right is listed the number of the postulate, which justifies that particular step of the proof. Table 2.1 Postulates and Theorems of Boolean Algebra. Postulate 2, A. X plus 0 equals x, B. X number 1 equals x. Postulate 5, A. X plus x equals 1, B. X hashtag x equals 0. Theorem 1, A. X plus x equals x, B. X hashtag x equals x. Theorem 2, A. X plus 1 is equal to 1, B. X number 0 equals 0. Theorem 3, Involution, x equals x. Postulate 3, Commutative, A. X plus y equals y plus x, B. xy equals yx. Theorem 4, Associative, A. X plus z equals x plus y plus z, B. xyz equals xy, z. Postulate 4, Distributive, A. xy plus z equals xy plus xz, B. X plus yz equals x plus y, x plus z. Theorem 5, De Morgan, A. X plus y equals xy, B. xy equals x plus y. Theorem 6, Absorption, A. X plus xy equals x, B. xx plus y equals x. Theorem 1, Ax plus x equals x. Statement justification number 1, x plus x equals x plus x. Postulate 2, B equals x plus x. X plus x. 5, A equals x plus 4, B equals x plus 0. 5, B equals x2, A. XX. Theorem 1, Bx hashtag x equals x. Statement justification. X hashtag x equals xx plus 0. Postulate 2, A equals xx plus xx. 5, B equals xx plus x. 4, A equals x number 1. 5, A equals x2, B. Note that Theorem 1b is the dual of Theorem 1, A, and that each step of the proof in Part B is the dual of its counterpart in Part A. Any dual theorem can be similar
in Part B is the dual of its counterpart in Part A.
In Part B is the dual of its counterpart in Part A. Any dual theorem can be similarly derived from the proof of its corresponding theorem. Theorem 2, Ax plus 1 is equal to 1. Statement justification. Jedna křížek x plus 1, x plus x, x plus x křížek 1, x plus 1 rovnítko postulate.
One number, x plus 1, x plus x, xx plus x number 1, x plus 1 equals postulate 2, b, equals plus 1, 5, a, equals 4, b, equals x plus x2, b, equals 1. 5, a. Theorem 2.
1 hashtag x plus 1, x plus x. Xx plus x number 1, x plus 1 equals postulate 2, b equals plus 1, 5, a equals 4, b equals x plus x2, b equals 1, 5. A theorem 2, b x number 0 equals 0 by duality. X hashtag X theorem 3, 10, equals X equals X. From postulate 5, we have X plus 1 and equals 0, which together define the complement of X. The complement of X is X and is also X. Therefore, since the complement is unique, we have X equals X. The theorems involving 2 or 3 variables may be proven algebraically from the postulates and the theorems that have already been proven. Take, for example, the absorption theorem, Theorem 6, ax plus xy equals x. Statement justification x number 1 x plus xy equals plus xy postulate 2, b4 a equals x1 plus y equals xy plus 1 3 a equals x number 1 theorem 2 a equals x2 b theorem 6 bxx plus y equals x by duality. The theorems of Boolean algebra can be proven by means of truth tables. In truth tables, both sides of the relation are checked to see whether they yield identical results for all possible combinations of the variables involved. The following truth table verifies. The first absorption theorem x0 0 1 1 y xy 0 1 0 1 0 0 0 1 x xy 0 0 1 1. The algebraic proofs of the associative law and De Morgan's theorem are long and will not be shown here. However, their validity is easily shown with truth tables. For example, the truth table for the first De Morgan's theorem, x plus y equals xy, is as follows: xy 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 0 0 0 1 0 1 1 0 1 0 1 0 1 1 1 0 x y xy 1 1 1 1 0 0 0 1 0 0 0 0. Operator precedence. The operator precedence for evaluating Boolean expressions is 1, parentheses, 2, not, 3, and 4, or. In other words, expressions inside parentheses must be evaluated before all other operations. The next operation that holds precedence is the complement, and then follows the and finally, the or. As an example, consider the truth table for one of De Morgan's theorems. The left side of the expression is x plus y. Therefore, the expression inside the parentheses is evaluated first, and the result then complemented. The right side of the expression is xy, so the complement of x and the complement of y are both evaluated first, and the result is then andied. Note that in ordinary arithmetic, the same precedence holds, except for the complement, when multiplication and addition are replaced by and or, respectively. Practice exercise 2.1. Using the basic theorems and postulates of Boolean algebra, simplify the following Boolean expression: f equals xyz plus xyz plus xyz plus xyz. Answer: f equals z. Practice exercise 2.2. Develop a truth table for the Boolean expression f equals xyz. Answer: xyz f 0 0 0 0 0 0 1 1 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 0 2.5 Boolean functions. Boolean algebra is an algebra that deals with binary variables and logic operations. A Boolean function described by an algebraic expression consists of binary variables, the constants 0 and 1, and the logic operation symbols. For a given value of the binary variables, the function can be equal to either 1 or 0. As an example, consider the Boolean function f1 equals x plus yz. The function f1 is equal to 1 if x is equal to 1, or if both y and z are equal to 1. f1 is equal to 0 otherwise. The complement operation dictates that when y equals 1, y equals 0. Therefore, f1 equals 1 if x equals 1, or if y equals 0 and z equals 1. A Boolean function expresses the logical relationship between binary variables and is evaluated by determining the binary value of the expression for all possible values of the variables. A Boolean function can be represented in a truth table. The number of rows in the truth table is 2n, where n is the number of variables in the function, the binary. Table 2.2 truth tables for F1 and F2 XYZ F1 F2 0 0 0 0 0 0 0 1 1 1 0 1 0 0 0 0 1 1 0 1 1 0 0 1 1 1 0 1 1 1 1 1 0 1 0 1 1 1 1 0. Combinations for the truth table are obtained from the binary numbers by counting from 0 through 2 and 1. Table 2.2 shows the truth table for the function f1. There are 8 possible binary combinations for assigning bits to the 3 variables x, y, and z. The column labeled f1 contains either 0 or 1 for each of these combinations. The table shows that the function is equal to 1 when x equals 1 or when yz equals 0, 1, and is equal to 0 otherwise. A Boolean function can be transformed from an algebraic expression into a circuit diagram composed of logic gates connected in a particular structure. The logic circuit diagram, also called a schematic, for F1 is shown in Figure 2.1. There is an inverter for input, y, to generate its complement. There is an AND gate for the term yz and an OR gate that combines x with yz. In logic circuit diagrams, the variables of the function are taken as the inputs of the circuit and the binary variable f1 is taken as the output of the circuit. The schematic expresses the relationship between the output of the circuit and its inputs. Rather than listing each combination of inputs and outputs, it indicates how to compute the logic value of each output from the logic values of the inputs. There is only one way that a Boolean function can be represented in a truth table. However, when the function is in algebraic form, it can be expressed in a variety of ways, all of which have equivalent logic. The particular expression used to represent the function will dictate the interconnection of gates in the logic circuit diagram. Conversely, the interconnection of gates will dictate the logic expression. Here is a key fact that motivates our use of Boolean algebra. By manipulating a Boolean expression according to the rules of Boolean algebra, it is sometimes possible to obtain a simpler expression for the same function and thus reduce the number of gates in the circuit and the number f1 xyy9zz Figure 2.1. Logic diagram for the Boolean function f1 xyz. Of inputs to the gate. Designers are motivated to reduce the complexity and number of gates because their effort can significantly reduce the cost of a circuit. Consider, for example, the following Boolean function, f2 equals plus xyz plus xy xyz. A schematic of an implementation of this function with logic gates is shown in Fig. 2.2a. Input variables x and y are complemented with inverters to obtain x and y. The 3 terms in the expression are implemented with 3 AND gates. The OR gate forms the logical OR of the 3 terms. The truth table for F2 is listed in Table 2.2. The function is equal to 1 when xyz equals 0, 0, 1 or 0, 11 or when xy equals 10, irrespective of the value of z, and is equal to 0 otherwise. This set of conditions produces 4 1s and 4 zeros for F2. Now consider the possible simplification of the function by applying some of the identities of Boolean algebra. F2 equals plus xyz plus y plus xy equals xc plus xy xyz xy xc y. The function is reduced to only 2 terms and can be implemented with gates as shown in Fig. 2.2b. It is obvious that the circuit in B is simpler than the one in A, yet both implement the same function. By means of a truth table, it is possible to verify that the 2 expressions are equivalent. The simplified expression is equal to 1 when xc equals 0, 1 or when xy equals 10. This produces the same 4 1s in the truth table. Since both expressions x9y9z x9yz xy9 xyz f2, a f2 5x9y9z1 x9yz1 xy9 xy xy9 f2z xe9 b f2 5xy9 1x9z Figure 2.2. Implementation of Boolean function f2 with gates. produce the same truth table. They are equivalent. Therefore, the two circuits have the same outputs for all possible binary combinations of inputs of the three variables. Each circuit implements the same identical function, but the one with fewer gates and fewer inputs to gates is preferable because it requires fewer wires and components. In general, there are many equivalent representations of a logic function. Finding the most economic representation of the logic is an important design task. Algebraic manipulation. When a Boolean expression is implemented with logic gates, each term requires a gate and each variable within the term designates an input to the gate. We define a literal to be a single variable within a term in complemented or uncomplemented form. The function of Fig 2.2 a has 3 terms and 8 literals, and the one in Fig 2.2 b has 2 terms and 4 literals. By reducing the number of terms, the number of literals, or both in a Boolean expression, it is often possible to obtain a simpler circuit. The manipulation of Boolean algebra consists mostly of reducing an expression for the purpose of obtaining a simpler circuit. Functions of up to 5 variables can be simplified by the MAT method described in the next chapter. For complex Boolean functions and many different outputs, designers of digital circuits use computer minimization programs that are capable of producing optimal circuits with millions of logic gates. The concepts introduced in this chapter provide the framework for those tools. The only manual method available is a cut-and-try procedure employing the basic relations and other manipulation techniques that become familiar with use, but remain, nevertheless, subject to human error. The examples that follow illustrate the algebraic manipulation of Boolean algebra to acquaint the reader with this important design task. Example 2.1. Simplify the following Boolean expressions to a minimum number of literals.
nx6y, xy mide xy xy.
xx2. X más xy igual a x más x.
Simplify the following Boolean expressions to a minimum number of literals. 1xx plus y equals plus xy equals 0 plus x.
Simplify the following Boolean expressions to a minimum number of literals.
nx6y, xy mide xy xy.
xx.
Simplify the following Boolean expressions to a minimum number of literals. 1xx plus y equals plus xy equals 0 plus xy equals xy. xx2. X plus xy equals x plus x plus y equals 1, x plus y equals x plus y. 3. X plus y equals x plus xy plus yy equals x1 plus y equals x4. xy plus xz plus yz equals xy plus xz plus yz, x plus x equals xy plus xz plus xyz plus xyz equals xy, 1 plus z plus xz, 1 plus y equals xy plus xz. X plus 5. X plus z, y plus z equals plus z, by duality from function 4. Y, xy, x. Expressions 1 and 2 are the dual of each other and use dual expressions in corresponding steps. An easier way to simplify function 3 is by means of postulate 4, b, from table 2.1, x plus y equals x plus y equals x. The fourth expression illustrates the fact that an increase in the number of literals sometimes leads to a simpler final expression. Expression 5 is not minimized directly, but can be derived from the dual of the steps used to derive expression 4. Expressions 4 and 5 are together known as the consensus theorem. Complement of a function. The complement of a function f is f and is obtained from an interchange of zeros for ones and ones for zeros in the value of f. The complement of a function may be derived algebraically through De Morgan's theorems, listed in table 2.1 for 2 variables. De Morgan's theorems can be extended to 3 or more variables. The 3-variable form of the first De Morgan's theorem is derived as follows, from postulates and theorems listed in table 2.1. A plus b plus c equals a plus x, let b plus c equals x equals ax by theorem 5, a, De Morgan, equals a, b plus c, substitute b plus c equals x equals a, b c, by theorem 5, a, De Morgan, equals a b c by theorem 4, b, associative. De Morgan's theorems for any number of variables resemble the two-variable case in form and can be derived by successive substitutions similar to the method used in the preceding derivation. These theorems can be generalized as follows: C equals a plus b plus c plus d plus f, a b c d c, equals plus b plus c d plus f a. The generalized form of De Morgan's theorem states that the complement of a function is obtained by interchanging n or operators and complementing each literal. Example 2.2. Find the complement of the functions f1 plus equals and f2 plus equals yz. xyz xyz xyz. By applying De Morgan's theorems as many times as necessary, the complements are obtained as follows: f1 equals plus equals x plus y plus z, x plus y plus z, xyz xyz, f2 equals x plus equals x plus x plus, y plus z, x plus equals yz xyz yz, yz, yzz, yyz. A simpler procedure for deriving the complement of a function is to take the dual of the function and complement each literal. This method follows from the generalized forms of De Morgan's theorems. Remember that the dual of a function is obtained from the interchange of n or operators and ones and zeros. Example 2.3. Find the complement of the functions f1 and f2 of example 2.2 by taking their duals and complementing each literal. 1 f1 equals plus xyz xyz. The dual of f1 is x and y plus y and z. Z, x. Complement each literal, x plus y plus z, x plus y plus z, equals f1 equals 2 f2 plus equals yz. xyz. The dual of f2 is x plus y and z, y and z. Complement each literal, x plus y plus z, y plus z, f2 equals. Practice exercise 2.3. Draw a logic diagram for the Boolean function f equals xy plus xy. Answer: xy x9y xy9 f. Practice exercise 2.4. What Boolean expression is implemented by the following logic diagram? xyf xy9 x9y. Figure PE 2.4. Answer: equals x plus f equals plus y equals xy plus yy equals xy plus xy xy y x xy xy xxy xxy. Practice exercise 2.5. What truth table is implemented by the logic diagram in Fig. PE 2.4? Answer: xy f001010100111. Practice exercise 2.6. Find the complement of the Boolean function f equals plus. Answer: f equals a plus bc plus a bc bc. 2.6. Canonical and standard forms, minterms and maxterms. A binary variable may appear either in its normal form, x, or in its complement form, x. Now consider two binary variables x and y combined with an operation. Since each variable may appear in either form, there are four possible combinations: xy, 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 and xy. Each of these four terms is called a minterm, or a standard product. In a similar manner, n variables can be combined to form two n minterms. The two n different minterms may be determined by a method similar to the one shown in Table 2.3 for three variables. The binary numbers from 0 to 2n, 1 are listed under the n variables. Each minterm is obtained from an n term of the n variables, with each variable being primed if the corresponding bit of the binary number is a 0 and unprimed if a 1. A symbol for each minterm is also shown in the table and is of the form mj, where the subscript j denotes the decimal equivalent of the binary number of the minterm designated. In a similar fashion, n variables forming an OR term, with each variable being primed or unprimed, provide two n possible combinations, called maxterms or standard sums. The 8 maxterms for three variables, together with their symbolic designations, are listed in Table 2.3. Any 2n maxterms for n variables may be determined similarly. It is important to note that 1. Each maxterm is obtained from an OR term of the n variables, with each variable being unprimed if the corresponding bit is a 0 and primed if a 1. And 2. Each maxterm is the complement of its corresponding minterm and vice versa. Table 2.3 Minterms and maxterms for 3 binary variables. Minterms, maxterms, xyz term designation 000 xyz m0x and ynz m0001 xyz m1x and ynz m1010 xyz m2 x and ynz m2011 xyz m3x and ynz m3100 xyz m4x and ynz m4101 xyz m5x and ynz m5110 xyz m6x and ynz m6111 xyz m7x and ynz m7. A Boolean function can be expressed algebraically from a given truth table by forming a minterm for each combination of the variables that produces a 1 in the function and then taking the OR of all those terms. For example, the function f1 in Table 2.4 is determined by expressing the combinations 001, 100, and 111 as xyz, xyz, and xyz, respectively. Since each one of these minterms results in f1 equals 1, we have f1 plus equals xyz equals m1 plus m4 plus m7 xyz xyz. Similarly, it may be easily verified that f2 plus equals xyz plus xyz plus xyz equals m3 plus m5 plus m6 plus m7 xyz. These examples demonstrate an important property of Boolean algebra. Any Boolean function can be expressed as a sum of minterms, with some meaning the O-ring of terms. Now consider the complement of a Boolean function. It may be read from the truth table by forming a minterm for each combination that produces a 0 in the function and then O-ring those terms. The complement of f1 is read as f1 equals xyz plus xyz plus xyz plus xyz xyz. Table 2.4 Functions of 3 variables. Function f1, function f2 000000011000011001010101011 10011111 f1 equals. If we take the complement of, we obtain the function f1. f1 equals x plus y plus z, x plus y plus z, x plus y plus z, x plus y plus y plus z, number m2, number m3, number m5, number z, x equals m0, m6. Similarly, it is possible to read the expression for f2 from the table. f2 equals x plus y plus z, 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 equals m0, m1, m2, m4. These examples demonstrate a second property of Boolean algebra. Any Boolean function can be expressed as a product of maxterms, with product meaning the ANDing of terms. The procedure for obtaining the product of maxterms directly from the truth table is as follows. Form a maxterm for each combination of the variables that produces a 0 in the function, and then form the n of all those maxterms. Boolean functions expressed as a sum of minterms or product of maxterms are said to be in canonical form. Sum of minterms. Previously, we stated that, for n binary variables, one can obtain 2n distinct minterms and that any Boolean function can be expressed as a sum of minterms. The minterms whose sum defines the Boolean function are those that give the ones of the function in a truth table. Since the function can be either 1 or 0 for each minterm, and since there are 2n minterms, one can calculate all the functions that can be formed with n variables to be 2n. It is sometimes convenient to express a Boolean function in its sum of minterms form. If the function is not in this form, it can be made so by first expanding the expression into a sum of n terms. Each term is then inspected to see if it contains all the variables. If it misses one or more variables, it is ANDed with an expression such as x and x, where x is one of the missing variables. The next example clarifies this procedure. Example 2.4. Express the Boolean function f equals a plus bc as a sum of minterms. The function has three variables, a, b, and c. The first term a is missing two variables. Therefore, a equals a, b plus b, equals a plus ab. This function is still missing one variable, so a equals ab, c plus ab, c plus c, equals abc plus ab c. The second term bc is missing one variable. Hence, bc equals bc, a plus a, equals ab c plus abc. Combining all terms, we have f equals a plus bc plus equals abc plus abc ab c abc. But ab c appears twice, and according to Theorem 1, x plus x equals x, it is possible to remove one of those occurrences. Rearranging the minterms in ascending order, we finally obtain f equals plus abc ab c abc equals m1 plus m4 plus m5 plus m6 plus m7. When a Boolean function is in its sum of minterms form, it is sometimes convenient to express the function in the following brief notation: f, a, b, c, equals 1, 4, 5, 6, 7. The summation symbol stands for the O-ring of terms, the numbers following it are the indices of the minterms of the function. The letters in parentheses following f form a list of the variables in the order taken when the minterm is converted to an end term. An alternative procedure for deriving the minterms of a Boolean function is to obtain the truth table of the function directly from the algebraic expression and then read the minterms from the truth table.
Minterms from the truth table. Consider the Boolean function given in example 2.4, f equals a plus bc. The truth table shown in table 2.5 can be derived directly from the algebraic expression by listing the 8 binary combinations under variables a, b, and c and inserting ones under f for those combinations for which a equals 1 or bc equals 0, 1. From the truth table, we can then read the 5 minterms of the function to be 1, 4, 5, 6, and 7. Product of max terms. Each of the 22 n functions of n binary variables can be also expressed as a product of max terms. To express a Boolean function as a product of max terms, it must first be brought into a form of or terms. This may be done by using the distributive law x plus yz equals x plus y, x plus c. Then any missing variable x in each or term is ORed with xx. The procedure is clarified in the following example. Table 2.5 truth table for FA, BCA, BCF 000000110100011010100 11011101111. Example 2.5. Express the Boolean function f equals xy plus xc as a product of max terms. First, convert the function into or terms by using the distributive law x plus yz equals x plus y, x plus cf equals xy plus xc equals xy plus x, xy plus c equals x plus x, y plus x, x plus c, y plus c equals x plus y, x plus c, y plus c. The function has 3 variables x, y, and z. Each or term is missing one variable, therefore, we combine the and of the missing term with its complement to the term where it is missing. X plus y equals x plus y plus zz equals x plus y plus y plus zz. Xx plus c equals x plus c plus yy equals x plus y plus c. X plus y plus c. Y plus c equals y plus c plus xx equals x plus y plus c, x plus y plus c. Combining all the terms and removing those that appear more than once, we finally obtain f equals x plus y plus c, x plus y plus c, x plus y plus c, x plus y plus c equals m0 to m4 m5. A convenient way to express this function is as follows: f x y z equals 0, 2, 4, 5. The product symbol denotes the andying of max terms. The numbers are the indices of the max terms of the function. Conversion between canonical forms. The complement of a function expressed as the sum of minterms equals the sum of minterms missing from the original function. This is because the original function is expressed by those minterms that make the function equal to 1, whereas its complement is a 1 for those minterms for which the function is a 0. As an example, consider the function f, a, b, c, equals 1, 4, 5, 6, 7. This function has a complement that can be expressed as f, a, b, c, equals 0, 2, 3, equals m0 plus m2 plus m3. Now, if we take the complement of f by De Morgan's theorem, we obtain f in a different form, m2 equals hashtag m3 equals hashtag. The last conversion follows from the definition of minterms and maxterms as shown in Table 2.3. From the table, it is clear that the following relation holds, plus m3, m0 equals 0, 2, 3, f equals m0 plus m0, m2, m3. m2 equals mj equals mj. That is, the maxterm with subscript j is a complement of the minterm with the same subscript j, and vice versa. The last example demonstrates the conversion between a function expressed in sum of minterms canonic form and its equivalent in product of maxterms form. A similar argument will show that the conversion between the product of maxterms and the sum of minterms is similar. We now state a general conversion procedure. To convert from one canonical form to another, interchange the symbols and list those numbers missing from the original form. In order to find the missing terms, one must realize that the total number of minterms or maxterms is 2n, where n is the number of binary variables in the function. A Boolean function can be converted from an algebraic expression to a product of maxterms by means of a truth table and the canonical conversion procedure. Consider, for example, the Boolean expression f equals xy plus xc. First, we derive the truth table of the function, as shown in Table 2.6. The ones under f in the table are determined from the combination of the variables for which xy equals 11 or xc equals 0, 1. The minterms of the function are read from the truth table to be 1, 3, 6, and 7. The function expressed as a sum of minterms is f, x, y, z, equals 1, 3, 6, 7, f, x, y, z, equals m1 plus m3 plus m6 plus m7. f equals 0, 2, 4, 5. Since there is a total of 8 minterms or maxterms in a function of 3 variables, what determineth missing terms to be 0, 2, 4, and 5, the function expressed as a product of maxterms is f, x, y, z equals 0, 2, 4, 5, the same answer as obtained in example 2.5. Table 2.6 truth table for f, x, y, xcx, yz, f, 0, 0, 0, 0 minterms, maxterms 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. Practice exercise 2.7. Find a product of maxterms expression for f, x, y, z equals 1, 2, 3, 5, 7. Answer: f equals 0, 4, 6, and f equals x plus y plus c, x plus y plus c, x plus y plus c. Practice exercise 2.8. Find a sum of minterms expression for f equals 1, 3, 4, 6. Answer: f, x, y, z equals 0, 2, 5, 7 equals xyz plus xyz plus xyz plus xyz. Practice exercise 2.9. Identify the minterms and maxterms of the truth table for f shown below. xyz f 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0. Answer: f equals 1, 3, 4, 6 equals 0, 2, 5, 7. Standard forms. The two canonical forms of Boolean algebra are basic forms that one obtains from reading a given function from the truth table. These forms are very seldom the ones with the least number of literals, because each minterm or maxterm must contain, by definition, all the variables, either complemented or uncomplemented. Another way to express Boolean functions is in standard form. In this configuration, the terms that form the function may contain 1, 2, or any number of literals. There are two types of standard forms, the sum of products and products of sums. The sum of products is a Boolean expression containing n terms called product. Terms with one or more literals each. The sum denotes the ORing of these terms. An example of a function expressed as a sum of products is f1 equals y plus xyz. The expression has three product terms with 1, 2, and 3 literals. Their sum is, in effect, an OR operation. y9x9z9yy. The logic diagram of a sum of products expression consists of a group of and gates followed by a single OR gate. This configuration pattern is shown in Fig. 2.3a. Each product term requires an AND gate, except for a term with a single literal. The logic sum is formed with an OR gate whose inputs are the outputs of the AND gates and the single literal. It is assumed that the input variables are directly available in their complements, so inverters are not included in the diagram. This circuit configuration is referred to as a two-level implementation. A product of sums is a Boolean expression containing OR terms, called sum terms. Each term may have any number of literals. The product denotes the ANDing of these terms. An example of a function expressed as a product of sums is f2x y++ equals y plus z x. This expression has three sum terms, with 1, 2, and 3 literals. The product is an AND operation. The use of the words product and sum stems from the similarity of the AND operation to the arithmetic product, multiplication, and the similarity of the OR operation to the arithmetic sum, addition. The gate structure of the product of sums expression consists of a group of OR gates for the sum terms, except for a single literal, followed by an AND gate, as shown in Fig. 2.3b. This standard type of expression results in a two-level structure of gates. A Boolean function may be expressed in a non-standard form. For example, the function f3 equals ab plus c, d plus e, is neither in sum of products nor in product of sums form. The implementation of this expression is shown in Fig. 2.4a and requires 2 AND gates and 2 OR gates. There are 3 levels of gating in the circuit. It can be changed to a standard form by using the distributive law to remove the parentheses. f3 equals ab plus c, d plus e equals ab plus cd plus c. The sum of products expression is implemented in Fig. 2.4b. In general, a two-level implementation is preferred because it produces the least amount of delay through the gates when the signal propagates from the inputs to the output. However, the number of inputs to a given gate might not be practical. XX Y9Z F1 F2 YZ9 X9 A. Sum of products. B. Product of sums. Figure 2.3 two-level implementation. A B B C D E C F 3 F 3 D C E A B 1 C D 1 E
A B B C D E C F 3 F 3 D C E A
B B C D E C F 3 F 3 D C E A B 1 C D 1 E B AB 1 CD 1 C. Figure 2.43 and two-level implementation practice exercise 2.10. Express the Boolean function f equals a plus bc plus ad as a sum of minterms. Answer: f equals 2, 3, 8, 9, 10, 11, 12, 13, 14, 15. Practice exercise 2.11. Express the Boolean function f equals xy plus xc as a product of max terms. Answer: f equals x plus y plus c, x plus y plus c, x plus y plus c, x plus y plus c. Practice exercise 2.12. Draw a two-level logic diagram to implement the Boolean function f equals plus bcab plus acd. Answer: a, b, c, d, b, c, 9 abfact 9. 2.7 Other logic operations. When the binary operators and or are placed between two variables, x and y, they form two Boolean functions, x hashtag y and x plus y, respectively. Previously we stated that there are 22 n functions for n binary variables. Thus, for two variables n equals 2, and the number of possible Boolean functions is 16. Therefore, the and or functions are only two of a total of 16 possible functions formed with two binary variables. It would be instructive to find the other 14 functions and investigate their properties. The truth tables for the 16 functions formed with two binary variables are listed in Table 2.7. Each of the 16 columns, F0 to F15, represents a truth table on a possible function for the two variables x and y. Note that the functions are determined from the 16 binary combinations that can be assigned to f. The 16 functions can be expressed algebraically by means of Boolean functions, as is shown in the first column of Table 2.8. The Boolean expressions listed are simplified to their minimum number of literals. Although each function can be expressed in terms of the Boolean operators and, or, and not, there is no reason one cannot assign special operator symbols for expressing the other functions. Such operator symbols are listed in the second column of Table 2.8. However, of all the new symbols shown, only the exclusive OR symbol is in common use by digital designers. Each of the functions in Table 2.8 is listed with an accompanying name and argument that explains the function in some way. 1. The 16 functions listed can be subdivided into three categories. 1. 2 functions that produce a constant 0 or 1. 2. 4 functions with unary operations, complement and transfer. 3. 10 functions with binary operators that define 8 different operations, and or, NAND, NOR, exclusive OR, equivalence, inhibition, and implication. Constants for binary functions can be equal to only 1 or 0. The complement function produces the complement of each of the binary variables. A function that is equal. Table 2.7. Truth tables for the 16 functions of two binary variables x, y, f0, f1, f2, f3, f4, f5, f6, f7, f8, f9, f10, f11, f12, f13, f14, f15, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 x, y. 1. The symbol is also used to indicate the exclusive OR operator, e.g., the symbol for the an functiones sometimes omitted from the product of two variables, e.g., x, y. Table 2.8 Boolean expressions for the 16 functions of two variables operator Boolean function symbol name comments f0 equals 0 null binary constant 0 f1 equals xy x hashtag y and x and yf2 equals xyx slash y inhibition x but not yf3 equals x transfer xf4 equals xy y slash x inhibition y but not xf5 equals y transfer yf6 equals xy plus xy exclusive or x or y, but not both f7 equals x plus y or yf8 equals x plus y, xty nor not or. f9 equals xy plus xy, equivalence x equals yf10 equals y complement not yf11 equals x plus y implication if y, then xf12 equals xx complement not xf13 equals x plus yxy implication if x, then y. f14 equals xy, xcy NAND not and f15 equals 1 identity binary constant 1. To an input variable has been given the name transfer because the variable x or y is transferred through the gate that forms the function without changing its value. Of the 8 binary operators, 2, inhibition and implication, are used by logicians, but are seldom used in computer logic. The and or operators have been mentioned in conjunction with Boolean algebra. The other 4 functions are used extensively in the design of digital systems. The NOR function is the complement of the OR function, and its name is an abbreviation of not OR. Similarly, NAND is the complement of and is an abbreviation of not AND. The exclusive OR, abbreviated XOR, is similar to OR, but excludes the combination of both x and y being equal to 1. It holds only when x and y differ in value. It is sometimes referred to as the binary difference operator. Equivalence is a function that is 1 when the 2 binary variables are equal, i.e., when both are 0 or both are 1. The exclusive OR and equivalence functions are the complements of each other. This can be easily verified by inspecting Table 2.7. The truth table for exclusive OR is F6 and for equivalence is F9, and these 2 functions are the complements of each other. For this reason, the equivalence function is called exclusive NOR, abbreviated XNOR. Boolean algebra, as defined in section 2.2, has 2 binary operators, which we have called and OR, and a unary operator, not complement. From the definitions, we have deduced a number of properties of these operators and now have defined other binary operators in terms of them. There is nothing unique about this procedure. We could have just as well started with the operator NOR, T, for example, and later defined and OR and not in terms of it. There are, nevertheless, good reasons for introducing Boolean algebra in the way it has been introduced. The concepts of and, or, and not are familiar and are used by people to express everyday logical ideas. Moreover, the Huntington postulates reflect the dual nature of the algebra, emphasizing the symmetry of plus and hashtag with respect to each other. 2.8 DEG tau logic gates. Since Boolean functions are expressed in terms of and, or, and not operations, it is easier to implement a Boolean function with these type of gates. Still, the possibility of constructing gates for the other logic operations is of practical interest. Factors to be weighed in considering the construction of other types of logic gates are 1. The feasibility and economy of producing the gate with physical components. 2. The possibility of extending the gate to more than 2 inputs. 3. The basic properties of the binary operator, such as commutativity and associativity. And 4. The ability of the gate to implement Boolean functions alone or in conjunction with other gates. Of the 16 functions defined in Table 2.8, 2 are equal to a constant and 4 are repeated. There are only 10 functions left to be considered as candidates for logic gates. 2 inhibition and implication are not commutative or associative and thus are impractical to use as standard logic gates. The other 8 complement, transfer, and or, NAND, NOR, exclusive OR, and equivalence are used as standard gates in digital design. The graphic symbols and truth tables of the 8 gates are shown in Figure 2.5. Each gate has 1 or 2 binary input variables, designated by X and Y, and 1 binary output variable, designated by F. The AND, OR, and inverter circuits were defined in Figure 1.6. The inverter circuit inverts the logic sense of a binary variable, producing the NOT, or complement, function. The small circle in the output of the graphic symbol of an inverter, referred to as a bubble, designates the logic complement. The triangle symbol by itself designates a buffer circuit. A buffer produces the transfer function, but does not produce a logic operation, since the binary value of the output is equal to the binary value of the input. This circuit is used for power amplification of the signal and is equivalent to 2 inverters connected in cascade. The NAND function is the complement of the AND function, as indicated by a graphic symbol that consists of an AND graphic symbol followed by a small circle. The NOR function is the complement of the OR function and uses an OR graphic symbol followed by a small circle. NAND and NOR gates are used extensively as standard logic gates and are in fact far more popular than the AND and OR gates. This is because NAND and NOR gates are easily constructed with transistor circuits and because digital circuits can be easily implemented with them. The exclusive OR gate has a graphic symbol similar to that of the OR gate, except for the additional curved line on the input side. The equivalence, or exclusive NOR, gate is the complement of the exclusive OR, as indicated by the small circle on the output side of the graphic symbol. Graphic symbol algebraic function truth table name XYFX and F5X. YFY0011010100100001 XYFX or F5 by 1 YFY001101011111 XF inverter XF5 X9 F01 10 XF buffer F5 XXF0101 XYF X y F5 XY 9F NAND 0011 0101 1110 X y F5
XYF5 XY 9F NAND 0
X y F5 XY 9F NAND 00
XYF5 XY 9F NAND 001101011110 XYF XYF5 X1Y 9F NOR 001101011000 XYF5 X% Y exclusive OR, XOR, XF5 XY91 X9 YFY 001101010110 XYF exclusive NOR or XYF5 XY1 X9 Y9F 5 X% Y 9 equivalence 001101011001 figure 2.5 digital logic gates. Extension to multiple inputs. The gates shown in Fig 2.5 except for the inverter and buffer can be extended to have more than 2 inputs. A gate can be extended to have multiple inputs if the binary operation it represents is commutative and associative. The and OR operations, defined in Boolean algebra, possess these two properties. For the OR function, we have x plus y equals y plus x, commutative, and x plus y plus y plus z equals x plus z equals x plus y plus z, associative. Which indicates that the gate inputs can be interchanged and that the OR function can be extended to 3 or more variables. The NAND and NOR functions are commutative, and their gates can be extended to have more than 2 inputs, provided that the definition of the operation is modified slightly. The difficulty is that the NAND and NOR operators are not associative, i.e., xty, tz, ytz, as shown in Fig 2.6 and the following equations. Ty, tz equals x plus y plus xz equals x plus xt, ytz equals x plus y plus equals y, zx y plus z equals xy plus xzz. To overcome this difficulty, we define the multiple NOR, or NAND, gate as a complemented OR, or AND, gate. Thus, by definition, we have xtytz equals x plus y plus z, xcycz equals xyz. The graphic symbols for the 3 input gates are shown in Fig 2.7. In writing cascaded NOR and NAND operations, one must use the correct parentheses to signify the proper xy, z5, x1y, z9xyx, yz, 5x9, y1z, xyz. Figure 2.6 demonstrating the non-associativity of the NOR operator, xty, tzxt, ytz. yxyxzz, x1y1z, 9, xyz, 9, a, 3-input NOR gate, b, 3-input NAND gate F5, ABC, 9, T, 995 ABC 1 to DBACE, C, Cascaded NAND gates. Figure 2.7 Multiple input and cascaded NOR and NAND gates. Sequence of the gates. To demonstrate this principle, consider the circuit of Fig 2.7, c. The Boolean function for the circuit must be written as f equals abc, d, equals abc plus d. The second expression is obtained from one of De Morgan's theorems. It also shows that an expression in sum of products form can be implemented with NAND gates. NAND and NOR gates are discussed further in section 3.6. The exclusive OR and equivalence gates are both commutative and associative and can be extended to more than two inputs. However, multiple input exclusive OR gates are uncommon from the hardware standpoint. In fact, even a two-input function is usually constructed with other types of gates. Moreover, the definition of the function must be modified when extended to more than two variables. Exclusive OR is an odd function, i.e., it is equal to 1 if the input variables have an odd number of ones. The construction of a three-input exclusive OR function.
Exclusive OR is an odd function, i.e., it is equal to 1 if the sequence of the gates. Multiple input and cascaded NOR and NAND gates. Sequence of the gates. To demonstrate this principle, Figure 2 C dB F5 A YXYXC, demonstrating the non-associativity of the NOR operator. XTI, TZ XT, YTZ. YXYXCZ, X1Y1Z, 9, XYZ, 9, A 3-input NOR gate, B 3-input NAND gate F5, ABC 9, D 995 ABC 1 D DBACE, C. Cascaded NAND gates. Figure 2.7 Multiple input and cascaded NOR and NAND gates. Sequence of the gates. To demonstrate this principle, consider the circuit of Fig 2.7c. The Boolean function for the circuit must be written as f equals abc, d equals abc plus d. The second expression is obtained from one of De Morgan's theorems. It also shows that an expression in sum of products form can be implemented with NAND gates. NAND and NOR gates are discussed further in section 3.6. The exclusive OR and equivalence gates are both commutative and associative and can be extended to more than two inputs. However, multiple input exclusive OR gates are uncommon from the hardware standpoint. In fact, even a two-input function is usually constructed with other types of gates. Moreover, the definition of the function must be modified when extended to more than two variables. Exclusive OR is an odd function, i.e., it is equal to 1 if the input variables have an odd number of ones. The construction of a three-input exclusive OR function is shown in Figure 2.8. This function is normally implemented by cascading two-input gates, as shown in A. Graphically, it can be represented with a single three-input gate, as shown in B. The truth table in C clearly indicates that the output F is equal to 1 if only one input is equal to 1 or if all three inputs are equal to 1, i.e., when the total number of ones in the input variables is odd. Exclusive OR gates are discussed further in section 3.8. Positive and negative logic. The binary signal at the inputs and outputs of any gate has one of two values, except during transition. One signal value represents logic 1 and the other logic 0. Since two signal values are assigned to two logic values, there exist two different assignments of signal level to logic value, as shown in Figure 2.9. The higher signal level is designated by H and the lower signal level by L. Choosing the high level H to represent logic 1 defines a positive logic system. Choosing the low level L to represent logic 1 defines a negative. XXYZY0000 F5 X% Y% ZZ 10 0 1 0 1 1 A using two input gates 10 0 1 0 1 0 1 0 11 1 1 x y z f5 x% y% z f 0 0 0 0 11 1 1 c truth table b 3 input gate figure 2.8 3 input exclusive OR gate logic signal value 1 H0 L1 A positive logic B negative logic figure 2.9 signal assignment and logic polarity. Logic system. The terms positive and negative are somewhat misleading since both signals may be positive or both may be negative. It is not the actual values of the signals that determine the type of logic, but rather the assignment of logic values to the relative amplitudes of the two signal levels. Hardware digital gates are defined in terms of signal values, such as H and L. It is up to the user to decide on a positive or negative logic polarity. Consider, for example, the electronic gate shown in Fig. 2.10b. The truth table for this gate is listed in Fig. 2.10a. It specifies the physical behavior of the gate when H is 3V and L is 0V. The truth table of Fig. 2.10c assumes a positive logic assignment, with H equals 1 and L equals 0. This truth table is the same as the one for the AND operation. The graphic symbol for a positive logic and gate is shown in Fig. 2.10d. Now consider the negative logic assignment for the same physical gate with L equals 1 and H equals 0. The result is the truth table of Fig. 2.10e. This table represents the OR operation, even though the entries are reversed. The graphic symbol for the negative logic OR gate is shown in Fig. 2.10f. The small triangles in the inputs and output designate a polarity indicator, the presence of which along a terminal signifies that negative logic is assumed for the signal. Thus, the same physical gate can operate either as a positive logic and gate or as a negative logic or gate. X, Y, Z, L, L, H, H, L, L, H, H, L, 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 H, A. Truth table with H and L, X, Y, Z, 0, 0, 0, 1, 0, 0, 0, 0, 1, 11, 1, C. Truth table for positive logic X, Y, Z, 11, 1, 0, 11, 1, 1, 0, 0, 0, 0. E. Truth table for negative logic figure 2.10x. Digital gate Y, Z, B. Gate block diagram X, Z, Y, D. Positive logic and gate X, Y, Z, F. Negative logic or gate demonstration of positive and negative logic. The conversion from positive logic to negative logic and vice versa is essentially an operation that changes ones to zeros and zeros to ones in both the inputs and the output of a gate. Since this operation produces the dual of a function, the change of all terminals from one polarity to the other results in taking the dual of the function. The upshot is that all AND operations are converted to OR operations, or graphic symbols, and vice versa. In addition, one must not forget to include the polarity indicator triangle in the graphic symbols when negative logic is assumed. In this book, we will not use negative logic gates and will assume that all gates operate with a positive logic assignment. Practice exercise 2.13. Draw the logic diagram corresponding to the following Boolean expression without simplifying it. F equals D plus BC plus D plus C, A plus C. Answer. A B C D B C F A 91 C D 1 C 9 D. Practice exercise 2.14. Implement the Boolean function f equals xc plus xy with A NAND and inverter gates and B NOR and inverter gates. Answer. F equals xc plus xy equals x plus c, x plus c, x plus y equals f equals x plus c plus x plus c plus x plus y. F equals xc, 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 f, xy, xc, xy. A NAND gates, B NOR gates, 2.9 integrated circuits. An integrated circuit, IC, is fabricated on a die of a silicon semiconductor crystal called a chip, containing the electronic components for constructing digital gates. The complex chemical and physical processes used to form a semiconductor circuit are not a subject of this book. Some CAD systems include Problem. Answers to problems. Answers to problems marked with asterisk appear at the end of a text. 2.1 Demonstrate the validity of the following identities by means of truth tables. A. De Morgan's theorem for three variables, x plus y plus z equals x plus and xyz equals y plus z xyz. B. The distributive law x plus yz equals x plus y, x plus z. C. The distributive law x, y plus z equals xy plus xz. Problems 93D. The associative law x plus y plus z equals x plus y plus z. E. The associative law x, yz equals xyz. 2.2 Simplify the following Boolean expressions to a minimum number of literals. A. Asterisk xy plus xy. B. Asterisk x plus y, x plus y. C. Asterisk xyz plus xy plus xyz. D. Asterisk x plus y, x plus y. B. E. I plus B plus plus C. ABC plus plus ABC plus F. C. ABC ABC. 2.3 Simplify the following Boolean expressions to a minimum number of literals. A. Asterisk xyz plus xy plus xyz. B. Asterisk xyz plus xz. C. Asterisk x plus y, x plus y. D. Asterisk xy plus xwz plus wz. E. Asterisk yz plus xw, xy plus zw. F. X plus c, x plus y plus z. 2.4 Reduce the following Boolean expressions to the indicated number of literals. A. Asterisk xyz plus y plus xyz to two literals. B. Asterisk xy, x plus z plus xy plus xyz to three literals. C. Asterisk x plus yz plus x plus yz to one literal. D. Asterisk w plus x, w plus y, x plus y, w plus xyz to four literals. Plus wy plus to two literals. E. wxyz wxyz. 2.5 Draw logic diagrams of the circuits that implement the original and simplified expressions in problem 2.2. C, E, and F. 2.6 Draw logic diagrams of the circuits that implement the original and simplified expressions in problem 2.3. A, C, and F. 2.7 Draw logic diagrams of circuits that implement the original and simplified expressions in problem 2.4. A, C, and E. 2.8 Find the complement of f equals xy plus yz. Then show that ff equals 0 and f plus f equals 1. 2.9 Find the complement of the following expressions. A. Asterisk xyz plus xyz. B. X plus y, y plus z, z plus x. C. Wx plus w, x plus y plus z. 2.10 Given the Boolean functions f1 and f2, show that a. The Boolean function e equals f1 plus f2 contains the sum of the minterms of f1 and f2. B. The Boolean function g equals f1 f2 contains only the minterms that are common to f1 and f2. 2.11 List the truth table of the function. A. Asterisk f equals xc plus xy plus yz. B. F equals plus abc plus plus abc abc abc. 2.12 We can perform logical operations on strings of bits by considering each pair of corresponding bits separately, called bitwise operation. Given two 8-bit strings A equals 11001010 and B equals 100100011, evaluate the 8-bit result after the following logical operations. A, asterisk and B, or C, asterisk XOR, D, asterisk not A cannot B.
2.13 Draw logic diagrams to implement the following Boolean expressions.